Yes. Yes, we can hear you.
Can you hear me?
Yes, we can hear you.
You cannot hear me. All right.
We can hear. Can, how can
Can you hear me now?
we can hear you, yes. Is that 这个需要调吗
Can you hear me?
Yes, yes, we can hear you. 他听到我们。这需要调吗？喂喂 ，Hello 喂。喂喂喂。
它没有在动那个音频呢。
对呀。喂喂。我先看看这个有没有。视频没问题。视频你切到另一个摄像头，得切回来。再切回来音频有问题。算了。喂。喂喂喂。可以可以，这可以。Yes, we can hear you. Can you hear us? You can hear us. Okay. Okay.
Can you see my slides?
Yes. Yes, we can see your slides. Yes.
All right. Let me see. All right.
Shall we start?
Sure. Sure.
Okay. Okay, let us start just on time. So, the first lecture of this afternoon session is, we are very happy to have Professor Mu-Chun Chen from University of California at Irvine. Professor Mu-Chun Chen, she is a great expert on particle physics phenomenology. So the title of her lecture is Neutrino Masses in Standard Model and Beyond Standard Model. Let's welcome her.
All right, so thank you very much. First of all, just like to say that it is a really great pleasure for me to give this lecture. And my regrets for not being able to be there in Beijing with everybody. So just want to give a sense of who is in the room. How many of you are working on, more formal theory, like string theories? Raise your hand. Just want to get a sense.
Formal theory, please raise your hand. String theory. You probably cannot see all of the theory.
Yeah, let me stop sharing. All right, how many of you are doing, more pheno, particle physics? All right, I see a few hands. And how many of you are working on neutrino theories? All right, there are a few more hands. All right, so I think this audience is very broad, so I will try my best. And let me see where my slides goes. Oh yeah. Great. All right. So I think this is actually a very exciting time for neutrino physics. Just to remind everybody, the discovery of neutrino oscillation, which indicate that neutrino have masses, was the subjects of the Nobel Prize in Physics in 2015, awarded to Kajita-san on behalf of Super Kamiokande collaboration, and to Professor McDonald on behalf of the Sudbury Neutrino Observatory collaboration. And this was awarded jointly to both of them both of the collaborations for the discovery of neutrino oscillations, which shows that neutrino have masses. Of course, subsequently, there's a breakthrough prize in fundamental physics, which was awarded to 5 neutrino experimental collaborations, which include Dial-Bay, Kamland, T2K and K2K, and Snow, as well as Super Kamiokande. And of course, the Breakthrough Prize recognized the major insights into the deepest questions of the universe. And it was awarded for the fundamental discovery and exploration of neutrino oscillations, which reveal a new frontier beyond and possibly far beyond the standard model of neutrino, far beyond the standard model of particle physics. All right, so the plan for today, I will go through neutrino masses in the standard model so that we make sure everybody is on the same page. I will go through a little bit of historic perspectives. I will introduce neutrino oscillation phenomena in vacuum. And of course, neutrino oscillation in matter is also a very important sort of aspect, but I don't think we will have time to go through it in detail. But we will go through the oscillation formulation, both for 2 flavors, 3 flavor, and a little bit of what goes beyond the 3 flavor neutrino oscillation. I will show a bit of the experimental evidence for neutrino oscillation, and we will talk about where we are in terms of the observational status, what we know, and what are the open questions that we still have in neutrino physics. So this will lay the groundwork for what we'll be discussing tomorrow, more on the theory of neutrino masses, namely neutrino masses beyond the standard model. So we go through a bit of the seesaw mechanism for neutrino mass generation, various beyond the standard model frameworks that predicts massive neutrinos. And I also hope to get to the fundamental origin or possible fundamental origin of flavor mixing and CP violation. And if time allows, I hope to also touch upon some cosmic connection, meaning baryogenesis through the progenesis. Right. All right. So here are 3 references which I draw upon from the lectures, and I think these are pretty good references if one wants to learn about this subject. All right, so a little bit of the historical perspective. For a very long time, it was thought that the atomic beta decay or heavy atoms goes through beta decay into light atom, and through this decay, it also emits the electron. So basically, these are 2-body decays. Through the energy momentum conservation, it was predicted that the electrons that were emitted must have a constant energy, right? However, the observed spectrum, instead of being a constant value, as you can see in this figure below on the right bottom corner of this page, instead of being a constant, what was being observed is actually a continuous spectrum. And therefore, this observed spectrum implies missing energy in the atomic beta decay. So the question was, why is a spectrum continuous? And namely, why the electron energy is not equal to the difference between the energy of the 2 atoms, right? So Pauli in 1930 invented this new particle, namely the neutrino, in order to explain this missing energy spectrum in beta decay. So what he was proposing was that instead of a 2-body decay, actually the atom went through a three-body decay, right? So in addition to emitting an electron, there's also the electron antineutrino that was being emitted. And given that now the electron and the antineutrino share available energy, this provide a way to explain the observed continuous spectrum of energies, and therefore, resolve this energy crisis. So neutrinos come into three flavors: electron neutrino, muon neutrino, and tau neutrinos. And the three flavors are defined through their weak interaction, meaning the electron neutrino is a particle associated with the weak interaction associated with the electron, and muon neutrino is associated with muon, etc., etc. Yes, so this is what I just said. And of course, in addition to this charge current weak interaction, that's how we define the flavor. Neutrinos also go through the weak neutral current interaction with the Z boson. All right, so I think I don't know whether this is easy to do because of the remote format, but this is sort of a little bit discussion just to warm up. Here I show the neutrino interactions, both the charge current weak interaction and neutral current weak interaction. What are the conserved quantum numbers in these interactions? Anyone?
So who wants to answer the question?
Yeah.
Question. Please come. Raise your hand. Who know the answer? Wants to? Okay.
All right. What are the conserved quantum numbers?
The lepton number?
Which lepton numbers?
Which lepton number?
Mm-hmm.
Neutrino, I mean electron, and with electronic neutrino.
Very good, very good. So lepton flavor numbers, right?
Yeah.
Meaning each couplings conserve the so-called lepton number, where we define the neutrino and the charged leptons to have lepton number of 1, where the antineutrinos and the charged lepton has -1, right? But if actually individual lepton flavor number, like what you were just saying, the electron lepton number, the muon lepton number, and tau lepton number individually are conserved in these interactions, right? All right. So from the precision test, electroweak precision test, we also have the information that there are 3 neutrinos. In particular, this is from the invisible decay width of the Z boson. All right. Okay. So for many decades, this was a really, really big puzzle, meaning the missing solar neutrino. The nuclear fusion reaction inside the sun, of course, produced a lot of energy. And in association with this fusion reaction, electron neutrinos were also produced. But while the electron neutrinos travel from the sun to the Earth, some of them were missing. In particular, the observed number of electron neutrinos is a fraction, only a fraction of the predicted number of electron neutrinos produced inside the sun, right? So yes, I just said this, number of detected neutrinos is less than predicted. And of course, the likely explanation is neutrino oscillation. All right. So the oscillation phenomena is actually very similar to a problem that I think most of you are familiar with in your classical mechanics, meaning the normal modes of the coupled pendulum, right? So what I show here is a set of coupled pendula where x1 and x2, this denote the individual displacement for each pendulum, right? But once we connect those pendula with a string, they are coupled. And therefore, the x1 and x2, these two displacements, are no longer the normal modes. So what are the normal modes in this system? Anyone? Yes, there's another question.
Students, what's the normal modes of this coupled pendulum system? How they oscillate? Do you know? Any?
I think there will be one normal mode they move together in the same direction, same phase, and there will be one they move opposite.
Right. So what do you mean by move out of it?
Means their velocities are always in the opposite direction.
Opposite
Like
direction.
they alternate like this. Yes.
Very good. So what that means is the actual two normal modes are linear combinations of x1 and x2. Right? In one case, like you said, it's like oscillate the same way, and the other case is they move out of phase in opposite direction. Right? So suppose these are two blocks with the same mass, then yes, the two normal modes then become x1 plus x2 and x1 minus x2 with a proper normalization, right? So, in the case of neutrinos, it's very similar, right? So what happened is, the electron, muon, and tau neutrinos, each of them, these are the flavor eigenstates. They are linear combinations of the mass eigenstates, mu1, mu2, and mu3. And of course, with different composition, right? And the amount of composition is, of course, from the oscillation experiment. That's how we determine, right, what compose to form electron neutrino, muon neutrino, and tau neutrino. Right, so for neutrino of a definite mass, meaning nu1, nu2, nu3, these are the states that propagate, right? So they have a definite oscillation length. But neutrinos are produced at accelerators, say at Fermilab, or at reactor, say at diol bay. It's the states that have a definite flavors are being produced, right? Because they were produced via the weak interaction. And once they propagate via their mass eigenstates, once they reach the detector, again, they are being detected via the weak interaction. And therefore, it's a state that have definite flavors that are being detected. All right. So, yeah. So basically, this is sort of the essence of the neutrino oscillation. All right. So again, this is just a little animation of what I just described, where at the neutrino source, their productions are, they are being produced via the weak interaction. And therefore, it is neutrinos of a definite flavor that are being produced. However, when they propagate out of the Schrodinger's equation, right? So it's based on their, mass eigenstates. Yeah, and therefore you get all this like superposition. Once neutrinos reach the detector, again, they are being detected by the weak interaction, and therefore neutrinos of a different flavor compositions may get detected compared to the flavors that are being produced at the source. given that different mass eigenstates evolve differently. Okay. All right, so this is a very simple, quantum mechanics calculation of the oscillation. Let's just take, say, two flavors, for example, nu e and nu mu, which are linear combination of two mass eigenstate, nu1 and nu2. And given that here I just have two flavors, there is only one mixing angle, theta. So I can write my two flavor states in terms of linear combination of two mass eigenstates. And with a simple calculation, one can show that the transition probability of one flavor into another flavor is given by this expression you see on the slides, namely the oscillation amplitude is given in terms of sine squared 2 theta, right? So the mixing angle determine the amplitude of the oscillation, where the delta m squared determine the oscillation length. All right. So and another point to note is that oscillation only measure the mass square difference, meaning delta m squared. It doesn't really measure the individual or the absolute mass of the neutrinos. Okay. All right, so delta m squared must be non-zero in order to have oscillation, right? So we do need to have the mass differences. All right, so again, this is just what I said. Where on the x-axis here, this is a distance that the neutrino travel, where the y-axis is the oscillation probability, right? So suppose I produce 100% muon neutrino at my source. Once neutrino travel some distance, some fraction of it oscillate and become the other flavor, nu e. And this oscillation amplitude is given by the mixing angle. And again, the oscillation length is set by the delta m squared. All right. So now let's just put everything back to the standard model. Of course, just remind ourselves, the standard model is a gauge theory based on the gauge symmetries of SU3, which is color, cross SU2 ellipse, cross U1 hypercharge. We have 3 generations of quarks and leptons, and of course, there are corresponding force carriers for the SU3, SU2, and U1. One thing which is puzzling is that all particles in the standard model, they come in both left-handed and right-handed partners, except for the neutrinos, right? So in other words, only left-handed neutrinos have been observed, or right-handed antineutrinos have been observed, but we haven't really observed right-handed neutrinos yet. Okay. All right. So this created a problem of neutrino mass generation within the standard model. So within the standard model, fermions get their, or quarks and leptons get their masses through the so-called Yukawa interaction. Basically, the left-handed and right-handed particles, they mix and interact with a Higgs vacuum interpretation value and acquire a VEV. How large their mass is would depend on how big this Yukawa coupling is. And given that in the standard model, there's no right-handed neutrino, there's no Yukawa interaction that we can write down for the neutrinos within the standard model. And therefore, standard model predicts massless neutrinos. Okay. All right. So here I'm just going to take a step back and just think about fermion mass generation, right? So there are 2 types of mass terms that one can write down generally. One is a so-called Dirac mass terms, which couples left-handed and right-handed fields, like what I show here. You can see in this equation. So this operator always involves two different fields. And the additive quantum numbers of these two fields are opposite. So what that tells us is that there are 4 degrees of freedom of the same mass, meaning we need 4 degrees of freedom to describe a Dirac fermion. Okay. However, there's another type of mass term called the Majorana masses, which couple a left-handed or right-handed field to itself. So again, you can see this on the slides here. So there can be only 2 degrees of freedom with the same masses, with the same mass, and the additive quantum number of these 2 fields are the same, and therefore it breaks all the U1 symmetries in this case. And given that this operator breaks all the U1 symmetries, what it means is we can only write down such mass term for neutral fermions. And of course, one good candidate for this neutral fermion is the neutrinos, right? So we cannot do this. We cannot write down the Majorana mass terms for the charged fermions, right? So we cannot do it for the electrons or quarks, but for neutrinos, there is this possibility. All right. So again, standard model implies exactly massless neutrinos because there are no right-handed neutrinos, and therefore neutrinos are massless within the standard model. Furthermore, there's no Higgs triplet, SU2 triplet Higgs in the standard model, and therefore there's no Majorana masses that one can write down that goes like SU2 triplet Higgs times the lepton doublets times the lepton doublets. All right, so that operator also doesn't exist. And given that standard model is renormalizable, again, we cannot write down Majorana mass term from the dimension 5 operator, meaning the Weinberg operator, HHLL. And therefore, neutrinos are massless within the standard model. However, unlike the fact that photons is massless, the massless neutrino prediction, this is somehow accidental, right? Because the fact that photon is massless, it is this prediction is a consequence of the fact that the U1 electromagnetism is a good symmetry, it's unbroken. But for massless neutrino, here we don't have such symmetry arguments, and therefore this prediction in the standard model is accidental. All right, so of course Higgs boson is discovered, and this is our new periodic table of particle physics, which now include the Higgs. And again, we have the 3 generations of fermions. And one peculiar thing is that as we go up the generations, the fermion masses increases, right? So this is sort of a very, one of the main focus of what we'll be talking about tomorrow, right? Just to address this mass problem, which of course also include the neutrino masses. All right, so what I show here, this is a mass spectrum of the elementary particles in the standard model. We just mentioned, as I go up the generation, the mass of the fermion increases. And given that there's given that in the standard model, the neutrinos are massless, I'm not putting it on this table yet. And yes, and of course, within the standard model, the Higgs mechanism generates fermion masses. However, it doesn't really explain this observed mass spectrum, meaning the pattern, like the ordering of these masses. We don't really have an explanation in the standard model. So in the standard model, all these masses are given by undetermined Yukawa coupling constants. And again, it predicts massless neutrinos. I just want to draw your attention that, right, the number of parameters that we need to accommodate all these masses actually is rather large. This is like a big fraction of the number of parameters that we have in the standard model. And therefore, right, we don't really have a really good understanding of the structure, right, of why the all these parameters must have those particular value to accommodate this pattern. And this actually account for a big fraction of the standard model parameters. So what that means is we don't really understand fundamentally why the standard model have its particular structure. All right. So in addition to this mass ordering, a related aspect is the flavor mixing, right? So within the quark sector, of course, we know quarks also mix. And what that means is the charge current weak interaction eigenstates of the quarks do not coincide with their mass eigenstates. And in other words, the weak interaction eigenstates are mixtures of the mass eigenstates. And they are connected to the so-called CKM matrix, which include 3 mixing angles and 1 phase. But given that neutrino masses are all degenerate in the standard model because they are all 0, what that means is the mass eigenstates coincide with weak eigenstates. And again, what that means is there exists accidental symmetries in the standard model, namely the electron lepton flavor number, muon lepton number, and tau lepton numbers. And given the existence of these accidental symmetries, what that means is there are no processes that can come across the family lines in the lepton sector. So as a result, standard model predicts no neutrino oscillation. It also predicts that there's no charged lepton flavor violating decays, such as mu E conversion or mu to E gamma. And of course, all these processes are the main focus of various experimental searches. And yes, and of course, in this case, the total lepton number is also conserved. And total lepton number here is defined as a sum of all the individual lepton flavor numbers. Of course, now we observe neutrino oscillation. What that means is neutrinos have masses, and therefore this opens up the possibility that their mass eigenstates do not coincide with their weak eigenstates. And of course, that's the case. So what that means is the lepton flavor numbers, Le, L mu, and L tau, are broken because we observe neutrino oscillation, and processes coming across family lines in the lepton sectors are now possible. And therefore, we observe neutrino oscillation, and the related question is whether there is also the lepton flavor violation in the charged lepton decays, right? So I just said there are major experiments searching for this decays, and this will be very interesting just to see what are the outcomes. And a different aspect is the total lepton number, right? Even though individual lepton flavor numbers might be broken, but their sum could still be conserved, right? So whether the total lepton number is conserved or not, this is related to the question about whether neutrinos are their own antiparticles. All right, so what if neutrinos have masses? If they have masses, then again, their mass eigenstates could have a mismatch with their interaction eigenstates. And that mismatch is now described by the so-called PMNS matrix, which includes 3 mixing angles and 1 CP phase if neutrinos are Dirac particles, right? So this would be just like in the quark sector. However, neutrinos could also be there's another possibility, meaning neutrinos could be so-called Majorana fermions, namely they are their own antiparticles. If that's the case, then there will be 3 CP phases, all right? So whether there are 1 or 3 CP phases, this depends on whether neutrinos are their own antiparticles or not. All right. So in the 3 neutrino case, if you have 3 neutrino flavor, this is sort of the form of the PM&S matrix, which generally can be decomposed in this way. So the very first 2x2 matrix, this is in the mixing in the 2-3 sector. Basically, this is sometimes called the atmospheric mixing. The second matrix there is, again, described as the so-called reactor mixing angle. And the third matrix there, it describes the 2x2 two-dimensional rotation in the 1-2 plane, and that mixing angle is dominantly probed by solar neutrinos oscillation experiments. And the very last matrix there, that's a diagonal matrix that contains 3 phases. And in particular, these are where the Majorana phases live, all right? So again, here we have 3 mixing angles, 3 CP phases if neutrinos are Majorana. But if neutrinos are Diracs, then there is the so-called Dirac CP phase delta. All right. So any questions up to now? All clear.
Any questions? Oh, sorry, there is a question.
Yes, please.
Could you explain in more detail why, if the neutrino is Majorana, there will be 3 CP phase?
All right, very good question. Right. So remember the way when we do the quark sector, the the CKM phase, right? We can rotate away the unphysical phases by redefining the quark fields.
Yeah.
Right, and that's how we rotate away 5 out of the 6 phases.
Oh.
Yes, but in the lepton sector, yep, go ahead.
So if it's a Majorana fermion, then it won't. So you can redefine this phase. So there will be to another phase left. So you can't just redefine the fermion. So
Yeah,
is that right?
Yeah, precisely right.
Okay.
Because remember,
thank you.
Majorana fermions, meaning particle and antiparticles, are identical, right? And if I were to do the rephasing, right, if I rotate a field by e to the I theta, I have to rotate for the antiparticle e to the minus I theta, right? But this would just violate that Majorana condition.
Okay.
Right. So basically, if particle and antiparticles are the same, that sort of forbids us to rotate away those 2 phases. That's clear?
Yeah. Thank you.
All right. Any other questions? Okay, very good.
No.
No. Okay, good. So this so you don't have questions, or I have a question for you. Here I show you this this parametrization of the lepton mixing matrix, right? So we have the first matrix, this atmospheric mixing angle in the 2-3 sector. The second matrix, that's the 2x2 rotation in the 1-3 sector, and the third matrix is a 2x2 rotation in the 1-2 sector. So my question for you is, is this parameterization unique or not? And if not, can you come up with another parameterization? So anyone wants to give this a try? Is it clear what the question is?
I think it's not unique because in the CKM matrix, we can have another parameterization. So yeah, it's not unique. And I think this just a standard parameterization, right?
Yeah.
So we can, maybe we can have a easy way to measure those mixing angles or the phase, I think.
Yeah, wonderful. So this is not unique, and actually you can just reorder, right? Reorder this, like how you can reorder these three 2x2 matrices. This three 2-dimensional rotation matrices, right? And yes, and it is shown in the standard notation just because of it's easier for the measurement consideration, but nothing is better than, it's just like convenience. All right, good. All right, so again, let me see whether I want to go through this because I have limited amount of time. All right, so I think I already did this oscillation formulation earlier in the 2-dimensional case, and that can be generalized to the 3-flavor case, very straightforwardly, right? So again, at the source, neutrinos are produced via the weak interaction. And if I were to write, right, so alpha here indicate the flavors, E, mu, or tau, and I here indicate the mass eigenstates, 1, 2, and 3, right? So again, neutrinos of different flavors are being produced, propagate via the mass eigenstates, and detected again via the weak interaction. And you generalize this to the 3-flavor case using the spatial relativity. What you can arrive at, or what you will arrive at, is the probability to observe flavor oscillation of alpha flavor into beta flavor according to this formula here. All right, so this U matrix, U alpha I, this is the elements in the PMNS matrix. Xij here, this is, right, this is basically the dependence on the delta M square and the time of the oscillation. All right, and very good. So I just leave it there. Yes, and if I turn off, all right, so the PMNS matrix here, notice we just said it could, right, depends on whether neutrinos are Dirac or Majorana. There could be one or two phases, right? So what that tells us is the PMNS matrix is complex, right? All right, so I think I can skip this. And yes, and another important point is that there are 2 types of experiment to detect neutrino flavor changes. One is called the appearance experiment, meaning measuring, say, I produce neutrino of alpha flavor, then I detect neutrino of beta flavor, right? So this oscillation, the transition probability of new alpha to new beta, if setup is like this is called appearance experiment. Where this appearance experiment is to measure the survival probability of new alpha. All right. So of course you can just work through the math, and the 2 probabilities are related, right? So again, here, what I show here is the two flavor oscillation probability in terms of the mixing angle and the delta M square. All right. So now, if I consider, right, putting the CP phase, meaning assuming the PMNS matrix is complex, the full transition probability is given as follows, right? You can see that on the slides. In particular, you see this second line here, which depends on the imaginary part of the so-called Yasko invariant, which is a product, imaginary part of the products of this four PMNS matrix elements. This is a parametrization independent CP violation measure of the amount of CP violation. So we have the equivalence, right, in the quark sector, the Yasko invariant in the quark sector. And here, this is how we define sort of the equivalent in the lepton sector. All right. So again, what I circle here, this is a Yasko invariant, which give us basically the amount of CP violation. And of course, what that shows is the oscillation probability of the neutrinos. And using the CPT invariance, we know for antineutrinos, the transition probability of nu alpha bar to nu beta bar should be the same as nu beta into nu alpha. And again, a little bit of math using the neutrino transition probability. The formula that we saw earlier, we have this relation of nu beta into nu alpha is equal to nu alpha into nu beta with u being complex conjugated. All right. So with this, we can then derive the transition probability for antineutrino channel, which basically introduce a minus sign on the term that depends on the CP phase. All right. So again, you can go through this math on your own, but this is how one go about deriving it. All right. So again, this is a question for you. Can CP violation be measured in disappearance experiment? Why or why not? All right. So again, let me just show you this formula. And remember, what does it mean by appearance experiment versus disappearance experiment?
Someone wants to answer the question? So how to measure the CP violation?
I see one hand in the back. One hand.
I think maybe use the probability of nu alpha to nu beta minus 2, the probability to nu alpha bar to nu beta bar, right? It's just
right. So the question is whether we can make use of disappearance experiment to measure CP violation.
I think it's yes, we can.
Can or cannot?
Why not?
Why not? So what does it mean by disappearance experiment?
I think we can measure. Use the nu mu to mu e minus 2, mu bar to mu e bar, right?
Right. So what is disappearance experiment? Is that nu mu to nu mu or nu mu to nu e?
Disappearance. It's not. Yeah. Yes. It's disappearance of neutrino. It's not the survival probability.
disappearance experiment meaning survival probability, right? The survival, new alpha to new alpha.
Yeah. And then then not. It's
Then
equal
not.
to 0, right?
It's equal to
Yeah.
0. What do you mean by equals to 0? Which one?
I mean the probability that we can use is equal to 0, because we cannot measure the mu nu to nu e, right? We can just measure the nu mu to mu nu. So when we use the probability mu nu to mu nu minus to mu nu bar to mu nu bar is equal to 0.
Right. Or another way to say it is that if I have the final state, right? If I measure survival probability, meaning beta and alpha are equal, then that dependence on the CP phase disappear. Is that clear? Right? And likewise, can the two Majorana phases be measured in the oscillation experiment? Again, this is a question for you, all of you. All right, anyone say yes? Raise your hand. Anyone say no? Raise your hand. All right, only see one hand, and the rest are. All right, so I think this is a very good exercise for you to do tonight, right? So again, remember how we write down the Majorana phases here, right? So the Dirac phase appear in that second matrix, what I call reactor, the delta phase. That's sort of that's a so-called Dirac phase, right? The equivalence of the phase in CKM matrix, right? But I also have two Majorana phases, what I call 512 and 513, which appear only in that diagonal phase matrix. All right. And this fourth thing is my PMNS matrix, right? So it's a sort of a nice exercise to do. Just to see whether there's any sensitivity, right, in this term that give us the this imaginary, right, this term in the second line that depends on the imaginary part of the products of the four PMNS matrix elements. Whether once you carry out these products, whether the Majorana phases survive or not. All right, so that's sort of your homework. And how much time do I have, or my time is up?
Actually, it's up. But if
It's
you
up.
want to, yeah, but you can have a few more minutes if you want.
All right, so very quickly, of course, we observe the oscillation, right? And one evidence is from the hemispheric neutrinos in Super Kamiokande, where we observe the upward going neutrinos. Let me see, what do I want to say? Yes, the upward going neutrinos, there's a deficit compared to the predicted flux, where the downward going neutrino, yes, downward going, yeah. So anyway, the half of the new mu disappear from those like upward going, where the downward going one, because the distance is sort of small, it's not enough time for them to oscillate, right? So this is a very, very solid evidence of the hemispheric neutrino. And we also have evidence from the solar neutrinos. Again, this is a very nice result from the SNOW experiments, which make use of 3 ways to measure neutrino fluxes. This include charge current interactions, elastic scattering, and neutral current interactions. And all three different type of measurements give us, all consistent result. So again, this is, a very, very solid evidence of the oscillation. And again, from the memory neutrino Kamland, again, we have very strong, we have very solid evidence of the oscillation. So, if we put all of this together from the solar part, the delta m square that is required to accommodate the observation is on the order of 10 to the minus 5 electron volt square, where for the atmospheric oscillations, we need 10 to the minus 3 electron volt square. And for there's another piece of evidence which is coming from OSND based at Los Alamos, which indicates a largest delta m square of 1 electron volt square, even though this result is sort of controversial, and there are subsequent experiments trying to confirm or refute it. So the question is, can we put all of this together? And that's sort of a whole discussion of the needs of stereo neutrinos, meaning going beyond the 3 neutrinos. Because if I have, 3 very different delta m square with only 3 flavors, it is not possible to accommodate, right? So I think I'm just going to stop here today. And tomorrow I will, show you where we are in terms of the measurement and going into the theory part, right? What would be the possible beyond the standard model theories that can naturally give rise to small enough neutrino masses, and what are the possible, what are the potential underlying new physics that can explain the large neutrino mixing. So I will stop here.
Okay, we thank Professor Chen for the very interesting and very pedagogical lecture. More questions for Professor Chen?
Thank you for this very inspiring lecture. And maybe this is a very trivial question, but I want to ask, what does it mean to have an imaginary mass? Does it have any relation with unitarity or anything else?
I did not mention anything called imaginary part. So where did that? Maybe I did not understand.
No, I mean, when you introduce a complex mass, that means there is an imaginary part of the mass, right? Meaning that's not real.
No, so that's just a phase. The actual physical mass is real.
Yes, but when you have a phase vector, doesn't mean it have a real part and an imaginary part.
No, that's just a phase associated with a field.
Okay, I see. Thank you.
Right, in just by, when I show the PMNS matrix, right, that's sort of attributed to the Majorana phases. But if it's a Dirac particle, that phase is unphysical.
And I have a naive question. So for Majorana neutrino, we can write down its mass term, but it is not allowed in standard model because it violates the SU2 times U1 symmetry. But why the Higgs triplet if we introduce the triplet, then it is allowed.
Right.
I'm wondering the reason.
Oh, it's just a SU2 product rule.
Pardon, SU2.
Just a group theory. So if I have, you're talking about the left-handed Majorana neutrino mass term, right? With just a lepton doublet,
yeah.
SU2 doublet, SU2 doublet, plus a SU2 triplet.
Yeah.
Right, and the product
So-
is a singlet under SU2.
Oh, okay. Thank you.
All right, so that's just
I understand.
SU2 group theory. Yeah.
Okay, I don't see any more questions. So let's thank Professor Chen again. So thank you very much.
Yeah, and see
She
you
will
tomorrow.
give us a second lecture tomorrow. Yeah,
Yeah.
see you tomorrow.
All
Thank
right.
you much. Bye. See you tomorrow. Yeah, so we're gonna take a few minutes break, and Professor Lee can prepare the lecture, next lecture. So you're gonna use your own laptop? It's a little complicated because we have many cables.
I can send you this.
Okay.
Fine. Sure. Okay then. Okay, so then it will be today is then today I revise tomorrow.
Yeah, of course.
So let's see.
Okay, thank you. But I need to ask our secretary for help. So no worry, you'll be ready in a few minutes.
So expected from this course thing. But I know you have the course around the sorry, meeting, so that I don't have the time to attend that. Oh, maybe. Well, I will definitely review the recordings. I get this content. I often say that I explain everything in much shorter time. I think it's different. Just talking is much easier and yes, exactly. So that's the better way to learn something. My own far away, but I'm there every day. So yes, I probably only can come in today, but tomorrow we have assignments. That's fine also. Then in the morning I will see the guys question around that. Yes, maybe you guys will give the talk in the morning. I attended this from my meeting. Oh, you did? Oh, yeah. Yeah, okay. That's the two courses. Okay, good.
Is this a change?
And I don't need a microphone.
Yes. This is
This
for
is
the
for recording. For you need this.
yeah. It's for the online live stream. This is my pretty like this.
这算不错。
Didn't work.
Click. Maybe you should click. Yeah.
现在是 full screen.
好像不是。
上刚才
那个下面 full screen 是看不到下面那一条的。啊，现在是。Backward, yeah. Okay.
All right.
Okay. So let's continue the second lecture of this afternoon session. We're very happy to have Professor Kim Yong Lee from BIMSA and the Korean Institute for Advanced Study. So Professor Kim Yong Lee, he's a world-leading expert on quantum field theory and string theory, in particular supersymmetric quantum field theory. So he's going to give us 2 lectures. The title of the lecture is Solitons in Quantum Field Theory and the Real World. Let's welcome him.
So some of you may know that I've been giving lectures in BIMSA for 12 lectures on solitons in quantum field theories. And when Junlian asked me to give a lecture, I have to think about what? Solitons in quantum field theory. Then I thought that's a bit boring because I talked about it. And I have to come back to real world, and then I put real world.
All of us attending the lecture on BIMSA.
Oh, that's good. Right. So, okay, so this is a brief outline. Quantum field theory, qubits, skyrmions, kinks, vortices, anyons, monopoles, instantons, and then stars. Very large bosonic star as a dark matter, which has been extensively studied in the last 4 or 5 years, or almost 10 years. Maybe you heard of this guy. This star is supposed to be like 1 light year big. Huge star, very thin, and it's around us, and we don't feel it. So that's why it's a dark matter. So this one sort of qubit is not exactly qubit, but that's why it's very easy to understand. But physics is, of course, very difficult to understand. But the principle is very easy to understand. So I'll talk about it tomorrow. So those are rough pictures of what I want to talk about. I know you guys went through a lot of talks and a bit tired with all things. And I'll just give us colloquium style talks, not much of details. So quantum field theory, I just heard a talk where neutrino oscillation is discussed, where you write down Lagrangian, you write down matrix, then you look at perturbative physics. So those are sort of quantum field theory, and we are describing nature using quantum field theory, and then we want to understand the theory and nature. So nature is right there, and this they say Himalaya from Tibet's perspective. I'm not quite sure about it, and I couldn't get rid of this marker. I didn't know about this. But anyway, nature is right there, and then we want to take very naive pictures. Then we want to detail the pictures. So nature is there, and then we want to have a theory from wrong theory, and it's always good to have a wrong theory. It's better than no theory. No theory means you have no idea, but wrong theory means you have an idea, even though it's wrong. And so nature is made of matters and forces. We just saw the matter, huge chunk of Mountain Everest. And it's matter and then forces. And we know those things. And the good old days, people divide into 5 elements, water, ions, or whatever. But we know now we divide into two things, matter and forces. That sounds pretty good. And also, metals are made of the atoms, nucleus, electrons. We know protons and the neutrinos, and nucleus, quarks and leptons, fermions. Those things are matters. And then electromagnetic forces, which then comes from photons, gravitational force coming from gravitons, and weak force coming from electroweak force from WZ and photons. And those are bosons or vector bosons. So it looks like these metals are made of spin half or spin 3 half fermions, and forces are given in terms of bosonic particles. And then, of course, there is a strong force coming from gluons. So those are the sort of things we know, and I just saw the previous speaker showed these similar pictures where metals and forces are divided in very simple forms in terms of quarks and leptons, and then vector bosons, and then gravitons and Higgs bosons. And so there are very simple objects which describe the nature which we see. I mean, think about 100 years ago, we had no idea, right? So we have many wrong tracks, but we are building up the correct theories. And the theory, in English word, the theory is very different from Chinese word, Iron. I don't speak Chinese, but Iron means you are arguing about some truth. It's very vocal, very auditory, using your ears. Iron means. On the other hand, the theory means it originates from, say, Greek word theater, which means having a picture. And because you guys have been working on physics, you know, picture is much more important than arguing about things. So even the idea of the theory and the iron is very different. In Chinese words are very different. And we are trying to build up the picture of the nature. So those are a current picture of our nature. And the theory is written in rather simple form. And we know what to fill in. Non-abelian gauge field, Yang-Mills theories, fermionic Majorana and Dirac fermions, and then Yugawa couplings, and the scalar field, and the potentials. Now, quantum field theory is a theory of identical particles, interacting identical particles. And it embodies Lorentz transformation and space-time translations, and is continuation of some classical field like electromagnetic field or scalar field or metric tensor, which are sort of bosonic field, and then like Dirac spinors or Majorana spinors, fermionic field. Then we start with some classical field, then we quantize it, and usually we just write down free theory first, which is if we quantize it, we get a harmonic oscillator normal modes, and then we get elementary particles, which are bosons and fermions. Then we add a bit of interactions between these particles, and then we do calculate, like perturbative method, Feynman diagrams, and denormalization. So we use the machine to calculate the physical quantities. And we are expanding our theories, trying to fit a sort of new experiment or that sort of things. And also, for given theory, we want to understand why those theories are like that. That's part of trying our work. So one of the things I've been telling theoretical physicists that we are not, let's see, slave of nature, and we want to understand the nature, but we want to pretend to be the master of the nature, in the sense that what if, say, quantumness is different? What if things are different? We can play with the theories, and we try to stretch whatever nature is offering us. We don't just accept it and produce the calculation or find the just right answer. We want to understand why so. So, you know, we are greedy people. We are not satisfied with what we have. We want to always expand our horizons. So one of the direction is this non-perturbative physics, which goes beyond the Feynman diagrams, beyond the perturbative physics. So the theories we wrote down could have an element or object, physical object, which is beyond the perturbative object, like elementary particles you are building up and interactions, but there are objects which you cannot build up from the perturbation of the theories. So those are non-perturbative physics, and solitons capture those physics. And today I'll talk about these solitons, which captures the non-perturbative physics of the theories. So let me start with QBAR. QBAR is so easy to understand, and it's so lately discovered in a way. Of course, it's 50 years ago. For you guys, it's long, long time ago. But it was compared history of quantum field theory, discovered quite late. So let me start with QBARs. Q here means charge. So QBAR was studied by Coleman in 1986. But before that, there are many works done. Especially, I remember as a graduate student like you guys in 1982 in Columbia, T.D. Lee, Professor T.D. Lee was working on QBARs. He got almost physics right, but not as neat as C.D. Coleman's. And you know, you can always look at the right angle, but you cannot get the answer not quite, and somebody else will come and get the right answer. But still, it's always have to try the new directions, and the QBAR is one of the directions. So suppose I have bosonic particles, and then short distance, so we have a repulsion, and little longer distance, it doesn't need to go to really Coulombic kind of interactions. Suppose you have attractive forces between them. Then particles, suppose I have them, then they don't want to come together too closely because of repulsion, but because of attraction, they want to hang around. So to capture this physics in simplest terms, let's think about some complex scalar field theory in, say, arbitrary dimensions, say 3 dimensions. And so there's complex scalar field, so there's U1 global symmetry, and then there's potential, which is, say, invariant under this U1 global symmetry. So, but this potential takes a rather complicated form because you want to capture the both short distance repulsion and long distance attractions. Now, scalar field interaction is, if you look, this pi square is mass term, pi force is 4-point interaction, and pi 6 is 6-point interaction. They are point-like interactions. But roughly, this because of this negative sign, 2 particles coming together, and it's attractive. And the pi 6 means 3 particles are coming together and repulsive. So roughly it captures the long distance attraction and short distance repulsion if you look at the dimension of the these coupling constants. So I drew the potential. Usually, either you are in broken phase or you have a symmetric phase. But this potential is sort of like you don't need to have a hump, but you can have a sort of because of this attractive force, you take this kind of pictures. And if you do Feynman rules, then you are looking at physics just around here. Now, this theory has a concept of U1 current. So here's the concept of current. And here, Fm phi, maybe, wait. oops. Scalar field is written in terms of magnitude and phase. So Fn script phi is a phase. So it's like a plane x plus iy in terms of radial coordinate and the phase. Then conserved current is f square del mu phi. So conserved charge is space integration of current density given in rather simple form. So now we are imagining some configuration of this complex scalar field, where scalar field takes in a large volume or volume V is constant inside, and then it goes to 0 outside. So we are doing, because the lowest energy of this potential is phi equal to 0, so we are in vacuum, but we are building up the configuration where scalar field magnitude is constant inside of volume V, then it goes to 0. Okay, so it's inside the F equal to F0 and outside 0. Now energy, so field is changing with space only around the surface. So let's ignore the surface because volume is more important. So energy will be given in terms of volume times this scalar field magnitude times pi dot square. Phase is rotating because it has to carry charge, and then times potential with F0. Now charge will be just F0 times phi dot times volume, because F is just constant and the volume is big, so V times F0 phi dot. Okay, so this will be F square phi dot square times volume, but I just said Q is equal to F square phi dot times volume, so I get rid of the phi dot and then write down Q square over 2F del square V. So this is like a centrifugal force in mechanics problem, angular momentum square over R square. But because now we have volume, we have to take care of volume part of it. So that's why volume, so this is like L square over R square, but volume goes downstairs because charge has volume in there. And then potential will be volume times this potential energy. So that will be the main part of energy configuration to energy for this configuration. Now we want to, for given F0, let's hold the F0, and we want to minimize the energy by adjusting the volumes, and it's very easy because this is 1 over V, so when volume is small, it's increasing, and this is decreasing, and when volume is big, this is decreasing and this is increasing. So you can find the minimum, and the volume is given in terms of charge divided by this quantity. Now plug this one into there, then we get an energy, which is charge times square root of 2U0 F0 over F0 square. So given F0, that will be the sort of minimum, given charge and given F0, that will be the minimum energy configuration. And then now we have to find the F0. Right, so given potential, we wrote down 2U0 over F0 is given in this function. And then we want to minimize this guy to get F0. Remember, this is mass term, and this attractive force, and that's repulsive force. So if I draw this quantity, then I start with m square, then it goes down, it goes up. And we want to make sure that this doesn't go to the negative, in which case things are more interesting. But let's keep minimum of this quantity to be positive. And then we choose, because we are minimizing energy, means we are minimizing this quantity, which is minimizing that. So we choose F0 to be at this value, and the value of this quantity to be m0 square. That's the definition of the m0 square. And then energy will be just m0 times q, which is some quantity, nothing to do with mass terms, but coming from this attractive force. And first of all, this is linearly growing with q, and also m0 is smaller than m because of this attractive force. So this is smaller than m times q. Now, if we go back, the mass of this particle, single particle alone at pi equal to 0 has mass m. But because of this attractive force, they are coming together and make a big ball, and the effective mass inside is m0, which is smaller than m. Okay? So you lower the energy by putting these multiple particles together, and the effective mass got reduced from m to m0, and so they make some lump, and that's called the cue ball. Now, of course, we didn't take into account the surface tension. Surface tension has the space gradient term and so on, but that's proportional to surface area, which is much smaller than volume. So if volume is big, then we can ignore it. But once you given volume, then you want to reduce the surface area. Well, lowest surface area for given volume is a sphere. So that's why we have a spherical ball, which is called the cue ball. So this field theory, classical field theory, captures very simple way, highly non-trivial, this collective view of large particles together and making a lump whose effective mass is much lower than real mass. This looks like a very simple, I mean, we study classical mechanics, you go to quantum field theory, at the first class, classical, I mean, this Yuan concept quantity and so on, then you can just make this calculation very simple.
By sphere, you restrict the space-time dimension?
No, well, not one dimension, but more than one dimension, circles and so on, right? Any dimension, right? Now, examples, water drops, raindrops. Well, let's ignore the water, airs, then the raindrops. Water drops, water molecules are attracted to each other, and they make a droplet. With some attractive force. Van der Waals force is repulsive in short distance, so that's why water droplet doesn't collapse the point. It just makes a shape, but they are attracted to each other, so they make a droplet. Us, we are cuboids. We are a bunch of molecules attracted to each other, stuck together, right? We can take many shapes because energetically, mass difference is tiny, tiny. But because the MC square is so big compared to the energy involved, but still, that attractive force is good enough to keep us in one shape. So it's, I mean, of course, we are not described by single complex scalar field. So, and also it's fermionic one. Its method is much more complicated, but roughly, simplest term is a cubal. Now, surface tension is very low. That's why we are not taking a spherical shape. And so on. Now, nucleus, which is made of protons and neutrons and strong interaction, those are again roughly cubals because they are attractive to each other, repulsive to each other in very short distance, but attractive to each other in little longer distance. So they can form a nucleus, and those are cubals. And it's of course more complicated than single complex scalar field, but in spirit, it's a cubal. So cubals are everywhere. Simply, we didn't have a word. Earth itself is a cubal, made of gas, rocks, and metals. And now in this case, we have gravitational attractions, which attracts everything. So it's lighter than if all the elements are far away in empty space. That's why they are all clumped together, and then they are stable.
What about the black holes?
Oh, that's an interesting point. Black holes are a little subtler. Yeah, you want to say black holes are cubal, but it doesn't have a cube. Right. So neutron stars, again, of course, neutrons, again, at gravitational force putting together, so it's a cubal. So it's very simple object. So when they are describing physicists, they say spherical cows. And cows are like, we simplify as a spherical shape. And it was something like that. So, you know, if all the methods we have, we simplify many ways. One of simplification is a cubal. I said that everything we see is a cubal in some sense. And it is a very simple idea, but very interesting idea. So let me look at the neutrons and protons in S wave where spin up and down. Then the forces are that in short distance is potential, repulsive, and long distance is attractive. That's why, again, these nucleus are taken shape. And that's why, not only that, now there is additional force, which is Coulomb repulsion, which makes this periodic table to be, you start from the one proton, then you go up to 118, and then that's it. There are no more nucleus because of the Coulomb repulsions. So it's called gauged qubits. So some of the charges are gauged, so that's why there are repulsive force. So even though you have an attractive force, you cannot keep up with, because the additional repulsion coming from Coulomb repulsion makes the qubit to disappear. So that's why this periodic table starts and then ends. So this is another view of the periodic table. There's a number of protons and number of neutrons, and the black one is stable. And usually we don't study nuclear physics anymore, right? Anybody take the nuclear physics course? Probably not.
I took it here in my
You took it, I took it. But what I didn't know was that for some proton number, there is no stable object. There's no black dots, which is, I didn't know. So some number of proton, whatever neutron number you throw in, you cannot make it stable.
Remember, some theory saying that there might be some stable island not related to this mass sequence.
Right, there could be some, and of course we know there is island if you go up, neutron stars. Okay. Those are nucleus in a way, but the force is there is not nuclear force, but it's a gravitational force. So it's empty for a while, then there is stable. Yeah, there could be some stable island here too. Yeah. So those are again qubits. Right. So now, any question about qubits?
When you introduce the potential for qubits,
right?
That shape is
right.
in the field strength space.
Right.
The horizontal axis is field strength.
Field. Yeah.
Yes.
Yeah.
But now you're making this analogy with distance. How should I relate this to?
Oh, okay, good. So when I wrote down the potential, scalar field is let's say 3 dimension, then has a dimension of mass. Now, the coupling constant, lambda pi 4 has dimensionless, but lambda pi 6 has a dimension per quantity. So that's why there is a scale coming in, right? But that's very simple matter. Yeah. So Scomians, Scomian is the English physicist. I don't think anybody. There's he's one of the guy who accompanied Poirier, the condensed matter physicist in English, condensed matter physicist in 1940s. Poirier, he's the first guy who estimated the weight of the critical mass of the uranium for nuclear bombs. And his estimation was about right. So that's why they knew nuclear bomb is possible. And he took 2 students to Los Alamos. And one of the guy was Fuchs, who was a Russian spy. And other guy was Scum. And he returned to UK, and we never heard of this guy until early 60s. He discovered a new way of writing down neutrons and nucleus. He had a new theory of nucleus, and about which I'll talk about. So, on his name, in honor of his name, the Scomian is named. So let's think about QCT, which is SU3 colored gauge theory with almost matrix up, down, strange quark with charm quarks and top quarks and bottom quarks. And QCD scale is about 1 GeV with color confinement. And then there is a ultraviolet high energy asymptotic freedom, which means coupling constant is running and equals to 0 in high energy limit. And also for this, suppose let's think of up and down quarks, they are lighter. If it's matrix, then the SU2 left cross the SU2 right, chiral flavor symmetry is there. But through the quark condensation of the left and right quark condensation, which is highly non-perturbative, this symmetry is broken to SU2 vector, which is a diagonal element of SU2. And during this spontaneous symmetry breaking, pions appear as Goldstone bosons. Now, this pionic field, Goldstone boson, can be captured because of these group structures in terms of SU2 element, which is given in terms of some coupling constant times sigma x plus I tau a pi a x, and those are field, and tau a is Pauli matrices. And then this Goldstone boson has a manifold, which is a 3-sphere, which is basically quotient of this group structure by this group structure, which is same as SU2, and SU2 group manifold is S3. So this scalar field, which we write down in 2x2 matrix, takes the expectation and value of the SU2 element, which means U dagger is equal to 1. Now, this field, we are looking at usual perturbative physics, so we are looking at fluctuation of this field around the pion field equal to 0, but we are looking at now non-perturbative physics, where this field as a map from 3-dimensional space to 3-sphere has a non-trivial winding numbers. So if you have this non-trivial winding numbers as a map from 3-dimensional space to SU2 group space, which is S3, and that is given in terms of third homotopy groups. And that's very well defined winding number. Same as circle going to circle, then you can wind the knot around the circle. Similarly, you can define these winding numbers. So suppose we have a non-trivial map, then what happens? Now, Lagrangian for this, which is invariant on the global part of SU2, is given in this kinetic term of pions. So this is like a pion kinetic terms. But this is not good enough. One can find that even though you don't have, you can ignore spatial time part of this higher order terms, because we can have a Lagrangian only use 2-time derivative, not 4-time derivative or 3-time derivative. We have to have only spatial derivative part of Lagrangian here, but this one is 4-time derivative. And one of the reasons we want to have this term is that this term is unique in the sense that it is invariant on the SU2 global symmetry, and it's just depending on derivative of the field. So those are unique terms we can add. I mean, there could be high order terms, but lowest unique terms. And with 2 elements, one can find an interesting configuration. So that's called the direct theorem. Let's think of energy, which is just depending on spatial derivative. Then we have a space integration of this spatial derivative of the U field. And then there's another, this quartic derivative terms. And so if we make a volume to be V, then length to the cube is length to cube. And then derivative will give us length to the minus 2. So together we get a length order times f squared. That's the kind of configuration we get. We are thinking about configuration with non-trivial winding numbers. So U is roughly fixed, but its profile, we have some length scale, and we are putting that length scale to be L. So we get estimating the energy. So this is a linear growing L. Now this guy has a 4 derivative, so it's L to the minus cube times L to the minus 4 times L to the cube. So we get a 1 over L. So roughly scale is the f square L plus 1 over g square L. So similar to Q-ball case, here again there is a balance because this goes to 0 when L goes to 0. So if I have non-trivial map and I shrink to 0 side, energy is equal to 0. On the other hand, this term, SCOM term, is growing because it's almost like short distance repulsion. When you are trying to collapse it, it bounces back. So this is 1 of L. So with this, you can balance the two terms and you can fix the size of this object. Not only that, there's one more topological term which Witten has discovered, and especially SU3 case easier. This with proper quantization, even though we start this all bosonic field, this fermion, this baryon, which we want to interpret this one as a baryon, becomes fermion. So you start this everything in bosonic field, then you can make a fermion out of it. About which I will tell more about it later on in magnetic monopole case. So that's what basis Jumino term does for you. So you start this all everything bosonic, then here is a fermion. You learned it in second year in quantum mechanics, but you didn't notice it. Remember when you do symmetric top, quantization of symmetric top, you have symmetric top going around, right? And then you quantize it, then you get all the angular momentum, including half integer angular momentum. And the symmetric top is bosonic object. What does it know about fermions? But if you quantize it, it generates fermions. And there are something about that related to magnetic monopoles. Even though you start with everything bosonic, you can create fermions. That's called the fermionization. And you start with fermions, then you can create bosons. It's called the bosonization. So something like the miracle kind of thing is happening in this process. So there's one more term which is complicated and topological, but which makes this topological object, skyrmion, which has a non-trivial winding number, to become a fermion. So SCOM originally suggested that this skyrmion as a baryon or proton. It doesn't have it doesn't have electric charge because you haven't coupled the electric charge yet. But still, it has isospin because pions are isospin vectors, and protons and neutrons are isospin spinors. So with these two terms, you can put into a computer and trying to find what is the configuration like that for different SCOM numbers. So that's the single skyrmion, spherical symmetric. So if you have a neutron or proton, you assume this sort of spherical symmetric up to spin half. But this baryon number 2 object, deuterium nucleus, right? And you don't suspect it has a donut shape, but it's some sort of exaggeration in certain limit that you can see a donut kind of shape. And 3, like a tritium or helium-3, it is like a tetrahedron shapes and so on. So this is how, even though number of the baryon is increasing linearly, the corner increases much faster. And that's the skymions. And this picture drawn by Nick Manton. And also there's a Hainan University in the Kaifeng.
Yeah,
Henan University. There's a Sven Gudnason. He's working on this. Right. So this skyrmion is again very interesting object, and there's generalization of this idea to condensed matter physics, and where people have discovered the magnetic skyrmions in experiment and so on. Now let's think about kinks, vortices, and anyons. So kink is, even though we can think about any dimensions, we can just simplify in 1 plus 1 dimension. Where suppose we have a single neutral scalar field with double potentials. And here, phi square term is negative, so that minimum of potential is at non-trivial phi equal to v and minus v. So there are two degenerate vectors. And then, because we have two degenerate vectors and we have one-dimensional space, either we can be in this broken space phi equal to v or phi equal to minus v. Then we look at perturbation around it. Then we get the elementary particles and then interactions between these elementary particles. Then we can build up the scattering amplitudes and so on. But instead, here we are looking at a non-perturbative object where at x equal to minus infinite, phi equal to minus v, and x equal to plus infinite, phi equal to v. So you are interpolating two vectors in given space. So that's a rather different kind of object. And we want to find this configuration. Among those configurations, we want to find the configuration which generates minimum energies. So we write down energy. Time derivative part is not important because we want to lower the energy, so we make it time independent. And then there's phi prime square. Prime means space derivative coming from energy of this guy, and potential terms. And we shift the potential and put this one in total squares. And the v square is related to m and lambda in this manner. Now, to minimize it, we have to make a stationary point of the energies. And one way of doing it is, of course, we write an equation of motion for this guy with the prime as a space as a time variables. Or we can do a little more, because we know this supersymmetric, all these things are hidden there. We put these two terms together into single squares, so pi prime, and then we take a square root of this, and then here's square. Then we each term will generate this kinetic and potential energy. Then we look at the cross terms, and cross term is a total derivative, and then integration of a total derivative. So it will be given in terms of boundary terms. So if you evaluate these boundary terms from plus infinity to minus infinity, then this generates the mass term of this object, because energy is something square plus minus some quantity m, which means energy is bounded by m. And this m quantity is given in terms of original mass terms, m cubed divided by lambda. So this object mass is already way bigger than small coupling, where coupling constant is very small. Then you can see coupling is, this mass is very big, which means non-perturbative, because it's 1 over coupling constant. Now this bound is saturated when this total square is equal to 0. And this equation is phi prime is, if you look at upper notation, v square minus phi square with square root of lambda over 2. So you can find the solution of this equation using tangent hyperbolic functions. And then as you change from x from minus infinity to plus infinity, phi interpolates minus b to plus b, exactly the satisfying boundary conditions. And that's the kink. Now, this very nice picture, but most of things, I said the cuboids are like this domain or which is surface, which relates inside and outside, and that's some sort of kink, right? It's more complicated version than this guy, but so I said we are kink cuboids, which means we have boundaries. So boundary, when you go through the boundary, there is some sort of kink where there's no particles, then suddenly there is some particles. In this case, of course, two vectors are degenerate, but cuboid case, the two vectors are very different, and you are interpolating two regions of the physics. And so this kink is the simplest version of that surface between the objects. Because, right, so everything we have, cuboids have surface, and then you have a change of the phase from one end to the other end, and the kink is sort of capturing the physics. Now vortex. Let's think about 2 plus 1 dimensional Maxwell theory coupled to Higgs field. So phi is complex scalar field, and the G square is coupling constant, and the d mu phi is del mu ordinary derivative minus I a mu phi is standard covariant derivative of complex scalar field, and then we have potential. Now, symmetry is spontaneously broken because phi has non-zero expectation value. In that case, phi vacuum can have value v, magnitude is v, but phase can be arbitrary. And our space, two-dimensional space, so boundary of two-dimensional space is a circle, and along the circle we can have a non-trivial winding. It's very different from Scomion case. Scomion case, we have three-dimensional space, then we are mapping from three-dimensional space to three-dimensional sphere. But here we are mapping from the, so that's almost vacuum solution, vacuum to vacuum. But here we are just looking at the configuration where spatial infinite scalar field has a non-trivial winding along the spatial circle, which means boundary is the vacuum to vacuum with non-trivial winding, but interior is not. So interior is more complicated, and that's the object we are talking about here. And those are called the vortices. So winding of the scalar field at spatial infinite is given to vorticities. And let's look at the energy again. So energy will be in terms of electric field square and magnetic field square, and the time derivative square and the space derivative squares, and potential energy. Now, time derivative, we ignore it. So electric field is equal to 0, and d0 phi is equal to 0. And magnetic field, because our space is two-dimensional, has only one component, F12. So we have F12 square and scalar field square and d1 phi square and d2 phi square. Now, we want to minimize the energy for given winding numbers. And the way you minimize it is through the, again, squaring the potentials. So we square this potential with F1 square, magnetic field square, and we square d1 phi square, d2 phi square in these holomorphic forms. Now you can square this guy with that and square this and get a nice cross term only if this pi4 coupling constant and this Maxwell electromagnetic coupling constant are identical. Only then you can square these two things. Of course, you can square always, but you can square this, and then there's additional cross term, and they cancel part of these cross terms only when lambda is equal to g squared. So with that combination, so we combined F12 with this potential square to potential square, and then we put d1 plus minus id to phi square, and then if you look at cross terms, and then you see only this part is surviving, which is v square over 2 times magnetic flux. And the magnetic flux is space integration of magnetic field. And again, this is a total derivative because the F12 is the curl of the vector field. So if we integrate over, then it will be given in terms of boundary value of the vector field along the boundaries. Now, we are trying to find the minimum energy configuration of this with given vorticity. So let's think about some general configuration where scalar field magnitude and phase is given simply in terms of vorticity. So there is a point, ZA is the point of the vortex, and then this phase changing by 2 pi as we go around. So it's argument of Z minus ZA, and then it's sum of the this argument. And that will be number R will be number of vortices. And then with this vortex configuration, we want to find the configuration where this two bound is equal to 0, and then energy is saturated by this magnetic flux. And this bound is called the BPS bound, and this equation which saturates these two equations, this being 0 and that being 0, is called the BPS equations. Now, detail is not that important, but this equation tells us that in complex notation, AI plus, if I put the phase, del I theta equals to epsilon ij del j log phi. And this goes to 0 at spatial infinite because the scalar field goes to 0 exponentially, where it's massive. Then phase of the scalar field and the gauge field, this value has to be locked together, so that vorticity, oops, sorry. So this vorticity, because of these equations, you can see that vorticity fixes magnetic flux, and magnetic flux is given by 2 pi r. So if you have a scalar field vorticity for finite energy configuration, magnetic field has to be 2 pi times vorticity. Okay. So that's why I call the magnetic flux vortex, and this has been observed in nature. So if you have superconductor, and then you put a magnetic flux in type 2b superconductors, then there are magnetic flux vortex going through the superconductor, and those configurations are exactly this configuration. Of course, they are not BPS, so things are more complicated equation, but the topology is identical. So magnetic flux vortex appears in superconductor are basically this object.
Time is almost up.
Time? Yep. Yep. Right. Thank you. So now 2 plus 1 dimension, there is more theories. Besides Maxwell theory, there is something called the Chern-Simons theories. And Chern-Simons theory is, if you look at quantized, then there's no photons, but it generates non-trivial dynamics on matter field. And especially Chern-Simons level has to be quantized to be integer to be gauge invariance. And then Gauss's law, which has to be imposed on dynamics, tells us that when you integrate over, and Gauss's law is the magnetic flux is proportional to charge, which means total magnetic flux is 2 pi times charge. That's U1 charge is what Gauss's law tells. And then because of Gauss's law, these objects are called the charge flux composite, and they carry non-trivial angular momentum. And you can do the vortex dynamics and so on, but interesting thing about this object is that for in symmetric phase, I can have a still charged object, then magnetic flux is given in terms of this quantity. And broken phase, I can have vortices, and then it has to carry charge because of Gauss's law. And then if you calculate the angular momentum, symmetric phase is q squared over 2k, anti-symmetric phase is given by that. So symmetric phase, q is integer, which means that q equal to 1 object is has a spin 1 over 2k. So if k is bigger than 1, or 1 is fermion, bigger than 1 is anyon, which means fractional spin. Now broken phase, you have fermions. When k equal, remember flux over 2 pi is always integer, so this is integer. K can be 1, 2, 3, 4. So when k is odd and the flux is 1 or 2 pi, you see this is a fermion. Okay, so broken phase, you can have fermion, no anyons. But in symmetric phase, you can have any spin 1 over 2k. So interesting case, k equal to 1, you can have a spin half in symmetric phase and spin minus half in broken phase. So tomorrow I'll talk more about anyons, which appears in also fractional quantum Hall effect. And then I'll talk about any actions, and then I'll talk about this ultra light scalar field, and also stars and dark matters. Thank you.
Okay, we thank Professor Lee for the very interesting talk. Any questions?
Can you somehow formulate the solitons in a quantized field? Like the solitons have interactions non-locally between solitons.
Right. So solitons are extended object. It's not singular object. So it's very hard to write down quantum field theories of solitons. Of course, you can have a soliton interacting with the ordinary perturbative part of dynamics. But some case you can write down interacting field theory of solitons. Very, very special case. So for example, 1+1 dimensional case, you can have I had a double kink, I mean double barrel potential, but I can have a sign like a potential, so periodic potential, and then I get a sine Gordon equations, and then in certain limit, it turns out that that's equivalent to Turing model, which is fermionic theory with 5-4 interactions. So there, domain or kink becomes fermion, and then meson becomes I mean, the small perturbative particle around at the bottom of the potential well becomes the bound state of fermions. So there's complete duality between weakly interacting soliton and strongly interacting fermions and vice versa. So there you can have it. Now, 3 dimensions, 3+1 dimension, again you can have it, which is n=4 for Yang-Mills series, where if my coupling constant is very big, W boson becomes very heavy, and monopole becomes very light. Then I can dualize the theory where I can have regarded magnetic monopole as a W boson of a new kind of theory, which is called the magnetic theories. And then you can have again this solitonic physics as a dynamical variable. So when you do perturbative things and the non-perturbative things, it's all depending on what range of coupling constant you are looking at. So as a quantum object, I don't care whether it's elementary particle or soliton, right? I have just quantum object. So in that sense, one can sometimes be successful about writing down.
Great, thanks.
Any other questions?
There are two
there.
Thanks for the lecture. I have a question that in which aspect does a soliton show its non-perturbative property? As I know, for example, in the n=2 supersymmetric field theory, we can have a non-perturbative term called the instanton. So
ZFF2, instanton, yeah.
Right. So the partition function can be decomposed into 3 parts: the tree level, one loop, and instanton.
Right.
So I want to know, is there any similar property that
yes,
the soliton can have the same?
Right. So suppose I have say partition function, then I do perturbative contribution. I mean, you can do the Euclidean time, so I can have perturbative contribution. Then I can have say magnetic monopole contribution. But problem is a different selection sector, because having a soliton is your Hilbert space has changed, because you are not building up from the vacuum structure. Then you are not building up the particle using the Fock space. Once you have soliton, especially topological ones, your Hilbert space has changed. So you have new Hilbert space. So you have to build up the partition function on that new Hilbert space. So that sense is non-perturbative. Now Q-balls are a little more finicky, because you put a lot of particles together, then they form the Q-ball. Then you could say it's sort of like a bound state of the particles.
Okay, thank you.
One last short question.
Is it possible to interpret some of the physical particles into the solution of the solitons, or some like the particles in the QCD? We have some maybe the glue ball or something. Is that can be interpreted as some soliton solution of the original theory?
So global, I don't think anybody now baryons scum generate scumions very nicely and it's perfect. No globals, we know without matter field, without quarks, QCD is still confining, so lowest energy state is global. It's not the gluons. Gluons in short sense physics. But globals is highly non-perturbative, but I don't think there's it's called nice semi-classical description. There's no effective field theory description of globals, which is more like solitonic description. So that would be very nice if one has that kind of description.
Okay, I see. Thank you.
Okay, let's thank Professor Lee for the very interesting, nice talk. We will continue tomorrow at the same time. Okay, thank you. So again, we are gonna take another few minute break and prepare for the next lecture.
All right.
Okay, nice talk. Thank you very much.
What time goes so quickly?
Yes.
1 hour, right?
Actually, 15 minutes because 1 hour
Right.
plus questions.
Right. Okay.
Thank you.
All right. So I'll see you tomorrow, maybe.
Yeah. See you.
Yeah.
Hear me? Some problem. Hi, Francesco. Can you hear me? You cannot? Can you hear me? Okay. Okay. Let's start maybe in 1 minute. Is that okay? We start in 1 minute, Francesco?
Just a sec.
Okay.
Just 1 sec because I'm trying to put the headphones.
Sure. Take your time.
Um, can you hear me like this? Can you hear me?
Yes.
Is it loud enough?
Francesco, yes, we can hear you.
Okay, wonderful. Yeah. So I can also see my screen, right?
Just a second. We have a problem. I just accidentally turned off the projector.
No problem.
So how to turn? Do you know how to turn the projector? 怎么开啊？用手动开吗？我不知道，我赶紧去找赵老师或者孟老师，你知道他们在哪？知道他们在哪？我去了。So Francesco, just a second. We have a little technical issue.关上了，很快就关了，怎么开就不好开了？
这个就是不知道问题了，我点那个 on 那个。
怎么没反应？
它 那个闪花应该就是我让那个谁一笔。哦，煮开了。但它现在难道是因为它过热了吗？或者像off一下，把这个东西关了，然后。
哎，好像。
哎，这个。那个
这个是这个，
对对对，
那个是图到外边。
我知道，但是只有一个遥控器。哎，好像我什么都没动。
不能有反。哦，好，可以了。
好了。
就是我关了然后开就行了。
对，但是要再关了再开，可能要花几分钟时间。Okay, sorry for the technical issue.
No problem.
Let's continue. So the next lecture is given by Professor Francesco Sanino. He's going to continue the discussion, effective metric description of quantum black holes. Let's welcome him.
Thank you. Hope you can hear me, and I will just since it's a continuation of the lecture on Monday, let me just fast reward a little bit what I said. And the logic is that we would like to be able to describe in as much as a model independent way quantum corrections of black holes. And I've already motivated that by saying that currently there are several approaches to quantum gravity, and we can't be sure which one of these is the correct approach. And therefore, it is actually paramount to have a model independent description of black holes, or in general of quantum gravity. Now, black holes are solutions, eventual solution of quantum gravity. And if quantum gravity does still have black hole solutions, quantum black hole solutions, so we can parameterize the correction in a general way, provided that we have a metric. And I started by introducing a static and independent spherically symmetric metric, and imposing only asymptotic behavior. So like flat, the metric should be flat to large distance, should provide an event horizon, and we don't know yet where is singular at the origin. If you upgrade your theory to be a quantum gravity theory, for the simple fact that to show that you have a singularity at the origin, you have to use the Einstein equation, the classical Einstein equations. So if you remove the Einstein classical equation, you only require the metric to be static, and therefore time independent, spherically symmetric, and to be flat at large distance, because we actually still observe that, and to feature an event horizon, then we can drop the possibility to have singularity at the origin. Okay, so we will no longer require the metric to be a solution of GR equation, but in that case we can without any doubt say that this is the most general metric you can possibly construct. Last time one of you asked, what about the spherically symmetric part? Why this does not get in any corrections? So this quantity cannot get any correction for a static spherically symmetric metric. However, H and F, which only depend on space, and that's why they are actually is a static. These two functions can be as general as you actually want, but if you require that they have to reproduce a great deal of the flatness at large distance and property of Schwarzschild, then property of your spherically symmetric, we have parameterized all the corrections into two functions that multiply, the term 2chi over z, and z has been measured in physical radius divided by the Planck length, and chi is the mass of the black hole measured in the Planck length. it's something well known that if you rescale the Schwarzschild metric, the Schwarzschild metric by this quantity becomes basically a scaling dependent. So there is only one scale in the problem, which is the Planck scale. I just want to stress that it's, sorry, I want to stress that the choice of the Planck mass and the choice of the Planck length it's arbitrary. I could have chosen another scale in the theory, right? Because we don't really know whether the quantum gravity theory sets on at the naive value of the Planck mass or equivalent in the Planck length. It could be much lower than that. There are, for example, a number of extra dimensional theories which would require a lower Planck mass, which means a larger Planck length. So this is just a rescaling. Now, these two quantities here, on the other hand, are two functions that we chose to be only functions of a physical quantity. You can choose any physical quantity you want. We have shown that mathematically proven that locally you can go from local observables like the Ricci scalar, or you could use the non-local observable like the physical distance, and locally you can map one into another. So you're not limited by your choice of the physical observables, okay? Now, for the sake of what I'm gonna discuss now, I've chosen as a physical quantity the physical distance from the origin of your extended object. And this physical distance is actually just a function of the metric itself. And since I'm using the physical distance, I only have to care about, and I'm looking at the physical distance from the origin to infinity, and the system is spherical, symmetric. I can actually just write it as a function of the square root of f. Now, this is a non-trivial self-consistent set of equations, right? Because the distance depends on the metric, and the metric depends on the distance via this parameter here. So clearly, I have to be able to do a little bit of work to self-consistently solve for this equation. Does it make sense? So I decided to work on the solutions on quantum gravity without even needing to know a theory of quantum gravity, provided the material of quantum gravity as a solution in metric. Is it clear, this as a logic? It's a very simple logic. Right? So simple that indeed you can derive universal results. When I mean universal, I really mean it. Okay, these assumptions are very, very mild if you think about it. Right. So because it is a non-trivial integral equation, I cannot solve it globally for the space-time, but I can solve it in certain regions of space-time. For example, close to the horizon, or for example, very far away from the horizon, where I know how the function, for example, f, can be expanded in local coordinates. Make sense? Yes. If you are more brave and would like to sew together these two these two regions, then you can get a little bit more out of it. Okay. But then you have to come up with more assumptions. All right. So let me start close to the horizon. So close to the horizon, I define the distance from the origin as the distance, a physical distance up to the horizon, plus a small deformation from the horizon. Okay. Rho now is still the physical distance, a displacement from the horizon. In the case of Schwarzschild, this is the Riedler coordinate, and the space is locally flat. But in general, this function f now can be expanded in a series in z. Z is the Schwarzschild coordinate, in z minus zh. And you see, this would be the only term that you have in classical gravity, okay, in classical GR. These terms now will come from your corrections to quantum gravity, and you don't know these coefficients, okay? The same you can do for h, since both have to have a killing horizon, and only a simple horizon we're assuming. That means that it must start with Z minus ZH. Okay, that's a must. But you can have higher orders. If you, for example, have a double horizon, then this term is equal to 0, and you start directly from this. And a paper will come soon to show how to handle this limit that, for example, emerges in charged black holes. Very good. So now I can go back and look at my two functions, right? And remember, I had written this as phi over little d, and little d is now d from the horizon plus the displacement. And I do an expansion, and I do an expansion, and I do an expansion in rho. Okay. So this now coefficient only contains physical quantities, because rho is a physical quantity. Therefore, the coefficient of it are physical, which means it will not change if you change your choice of coordinates. And the leading term, I mean, the constant term is just the Schwarzschild radius at the horizon. Now you have two sets of physical quantities. One are the ones that you need to include to describe displacement for rho, and the other one is what you need to do to the displacement for f, and the other one is displacement for the h function. So the set of quantity of psi n and theta n will describe for you wherever theory of quantum gravity you have close to the horizon. So if you do an experiment, say you measure these quantities, then you uniquely fix the theory of quantum gravity beneath. Make sense? If you don't get an answer, I assume it does. Once I know f as a function of z, I can now invert it to get rho, exactly from this equation here, okay? From this equation here, now I put f inside, and I get my, I write this as dh, right, plus rho, and then I can invert for rho, and if I invert it for rho, you see that I get the first term, which is what you will get also in Schwarzschild, but now you get corrections from it. So I can not only write rho as a function of z, but I can also write z as a function of rho. This is a locally invertible. And you have zh plus the famous quadratic term in rho, which tells you indeed that the space around the black hole of GR black hole is actually a Riddler space, and it's locally flat. But of course, you will have also this other term. Then you will have also terms which are rho to the 6. I want you to observe that this particular combination of terms are now physical. They don't depend on the way you've written the coordinate. Each one, f1 or f, so f1 at h is the first derivative of f at the horizon with respect to the z coordinate. f2 is a second derivative of f at the horizon as a function of the Schwarzschild coordinate. But this particular combination, f1 times f2 divided by 96, these are independent of the way you've written the coordinates, because, I mean, they have been expressed now in terms of rho. So I can now re-express f in terms of physical coordinates. And again, these parameters now are physical. So this is the game that you're getting, right, in writing like this. So now that you do that, I can look at other physical quantities, like, for example, the Ricci scalar. And you see, this is the Ricci scalar for arbitrary distances from the horizon. But now I want to see what happened close to the horizon. And I discovered that f1, very close to the horizon, has a divergence in 1 over rho. Now, as a divergence that depends on the first derivative of the function phi at the horizon. In the classical Schwarzschild case, this is 0. In fact, R is 0 in the entire space-time. So you could say that the simplest, diagnostic, whether you have quantum corrections or correction to Schwarzschild, is that you observe a non-trivial curvature in space-time, right? Because Schwarzschild basically predicts R equal to 0. But this, if I want to have a well-defined black hole, any physical observable must be well-defined. Therefore, I immediately have to predict that phi 1 is equal to 0. Phi 1 is actually directly related to the first coefficient of the expansion you've seen before for F. And the same is actually for H. So you have these two universal constraints. Whatever metric, and we're going to see some metric that actually had violated this constraint, even though they've been highly used in the literature. And you will wonder how come they've been used in the literature, even though these metrics were actually wrong. So these coefficients tell you that this diagnostic tells you that expressed in terms of a physical distance, you have universal constraints on the physical parameters in the expansion of your method. Now, I don't want to bore you, but if you impose fineness for the Ricci and impose positivity bounds for the metric functions, meaning that your function must be well-defined and positive, you find several universal constraints or physical conditions at the event horizon. And these are actually xi1, θ1 equal to 0, already motivated for you, and then you have other conditions, right? These conditions are all have to be satisfied by all the parameters of the theory. And if you have a metric, then you can compare with these coefficients. You can calculate them. We have in the papers, we show it to you how to, from any metric, you can calculate these physical quantities. And if these conditions are not respected, then the metric you've written is not a black hole. Okay. Make sense? But now we have written, hopefully it does, now that we have written the metric in terms of physical quantities, I would like to know how many independent parameters do you need to do to have at a fundamental level to describe the Hawking temperature. That would be great, right? So let's see. At the classical level, so a little bit of phenomenology of it. So in 1974, Hawking derived his own temperature. Okay? The temperature of a black hole is basically directly proportional to the inverse of the mass of a black hole. The largest, the heaviest is the black hole, the coldest the black hole is. It's a bit counterintuitive, but actually that's the way it is. And if you now power through and try to calculate how long does it take for a black hole to evaporate, because if a black hole has a temperature, eventually it's a black body, and if it's a black body, it will actually emit. But the evaporation time is directly proportional to the cubic value of the mass of the black hole, which if I normalize it to the sun, you find out that for any black holes which are a mass of the order of the sun mass, you will take 10 to the 67 years before the black hole completely evaporates. Now, the universe, the age of the universe is 10 to the 10 years. So there is no way that a black hole evaporates within the time span of the universe. So this means that you have to have smaller black holes. Smaller black holes are, for example, predicted like primordial black holes. Now we don't know the density of that, but I mean, bounds have been set for this black hole, for example, generated by quantum flotations at the beginning of the universe. You could also have, asteroid-sized black holes. I mean, we are working on something interesting about that, but they all require exotic metrics. Okay, make sense? Is it clear? So for any mass larger than a sun mass, we will have a hard time seeing testing the Hawking temperature, but even actually seeing. So the only possibility is if the black holes that we have are produced copiously and their masses are smaller than or of the order of a fraction of an asteroid. Good. How do you calculate the Hawking temperature? There are many ways of doing that. I would say the simplest one is through its own definition via surface gravity. So if you say that the temperature of a black hole is directly related to surface gravity, then you know the surface gravity is directly calculated from knowing the Killing vector your space. And once you plug in this, you get this famous relation that chi-square is proportional to f times f1 square, I mean h1 divided by h at the horizon. So if you want to calculate the at the horizon, at the end of the day, this gives you the Hawking temperature. The Hawking temperature is indeed calculated directly at the horizon. So you have to take this formula and expand it around the horizon. So you need to know the first derivatives for f and h. Okay. But you know, if I just say that f and h can still depend on, in principle, on an infinite number of parameters of the theory, right? So I want to know how many parameters are really needed at your quantum level to have a universal description of the Hawking temperature. All right, at the classical level, only one parameter is needed, and it's the physical mass. Now, if you take our metric written in terms of the physical coefficients, you find out that you only need the information about the how big is the size of your black hole, and then two more parameters. So three physical parameters are sufficient to encode information from any quantum theory of black holes. Okay. So not only the mass, but two more are needed, which I thought it was pretty cute thing to know. And in principle, you can, if one day ever able to measure it, you can actually constrain different theories of quantum gravity. Any questions so far?
No questions.
Very good. So how about the entropy, right? So you also heard about the entropy of a black hole. So for the entropy, let me kind of try to get on the same page first. There are many definitions of entropy, right? So this one you studied in school when you were doing freshman physics. And now, as you get a little bit older, then you also be hearing different type of entropy. I would say one which, sorry, are there questions?
No question.
Okay. So one type of entropy that is very popular now is what is known as fine-grained entropy, and is obtained via the von Neumann definition of it. So if you give me a quantum system and you're able to calculate the density matrix, well, just take the trace rho log rho, put a main signs in front of it, and this is your entropy. This is the, I would say, the entropy that describes and it knows about all the quantum states of your theory. You can also show that it's unitary under time evolution, which means if you take your density matrix and through your Hamiltonian, you evolve your states, you can show that this entropy is unitary, right? It's well defined. Any practice quantifies our ignorance about the quantum state of the system. However, that's not what you learn in school. What you learn in school is something which is a little bit less than the full von Neumann entropy. What you actually learn in school is the coarse-grained entropy. So you have to consider a subset of observables. For example, the total energy, the free energy, the pressure, the volume. Remember when you studied the thermodynamics, right? You had a limited number of observables. You did not have the entire system, right? Isn't it beautiful? I mean, just to go back and review what you've done, but in a slightly different context. Very good. So, but now I say, okay, consider some density matrices rho, but I put a tilde on it, such that if you calculate the average of your observable on rho tilde, you get the actual value, as if you knew the correct matrix density. Of course, this is a subset. Rho tilde doesn't have the full knowledge of your quantum system, as a limited knowledge. That's why it's called coarse-grained. Right? Now, maximize this, calculate the entropy using rho tilde, and maximize it in order to get the largest possible value of S. Now, this is the S that you have learned at school. This is a thermodynamic S with A, capital AI, for example, the energy and the volume. Now, this one is not unitary, because remember, to be unitary, you have to look at the full density matrix. You have to explore the entire quantum system. You can't just take a subset of the quantum system. As soon as you take a subset of the quantum system, the system is no longer unitary, right? Make sense? Is it clear? And therefore, it obeys the second law of thermodynamics, and it always increases under atomic motion. So this is the entropy that you loved and learned once you were studying freshman physics, in particular thermodynamics. And this is the one that Hawking used. So Hawking said, okay, let me use the first law of thermodynamics. Remember, in the first law of thermodynamics, you say the change in the heat is proportional to the change in the entropy, with the constant of proportionality to be the Hawking, to be the temperature. That's what happens in thermodynamics. So on the other hand, in a black hole, the equivalent of a change, the equivalent of the change in mass, right, is directly proportional, is now what you can consider the change in heat, okay? And therefore, you apply the same law of thermodynamics by saying, okay, if I exchange the change in heat with the change in mass, then I can still have TdS, but now my T is the temperature of the black hole, which I call it the Hawking temperature, because in honor of Hawking. And this is the way, you know, that Jim Carrey will say in the famous movie, the way the cookie crumbles. Right? Now I can actually go back and say, you give me the temperature as a function of the mass, which is exactly what was given by this law. And then I apply this equation, and I can get the entropy. Now remember, the entropy is defined at up to an overall value, right? Because it's an integral, and I don't know the overall value of the entropy. But the temperature in general, remember, in the case, now we have proven that the temperature, Hawking temperature for a generic quantum system, it only depends, it depends on only three parameters, but three parameters can all of them depend on the mass. So you depend on the distance, psi2 and theta2. I mean, these two are related, so it's basically just one parameter. So in order for me to be able to calculate the entropy, I need to know the dependence on the physical parameter on the mass of the system. And I have to actually do much more than that. So this is the price to pay to go from the temperature to the entropy. You actually need to know more for that. So the entropy can only be evaluated if you actually have a model. But then, of course, it's a model dependent. Is it clear?
Yes, it's clear.
And this is to be expected, because you need information on the entire quantum state, which we don't have with an effective description. Now I want to prove it to you that if we go in the classical regime, so which means we switch off all the quantum corrections, of course I recover the Hawking area law, right? So if you set psi2 equal to theta2 equal to 0, which is indeed the classical limit, and of course your quantum, your physical distance from the origin now becomes your classical distance from the origin, which is pi chi. Remember, chi is the mass measured in the Planck mass. ZH is the Schwarzschild radius. You plug it back here, you get the famous, our temperature recovers the standard Hawking temperature. You plug it back in the formula for the entropy, you get the famous result that the classical entropy is up to an overall undecidable constant is directly proportional to 4 pi, the mass square of the black hole, in unit, in this case, of the Planck mass. And this is the way the model or the effective model is able to naturally go over the classical regime. Good. So far, I hope I have convinced you that we using the event horizon finiteness conditions for every physical quantity on 5 psi, we were able to get not only a general expression for the Hawking temperature, but universal constraints on the form of the quantum corrections to any spherically symmetric static black hole. Good. So now I want to prove it to you that these constraints are useful. Right? So every time you do something, you have to show that it's mathematically consistent, it is predictive, and at the same time useful. For example, will constrain models of quantum gravity. And I'm going to do the third of this. I'm going to prove the power of constraints. So imagine that you are two of our esteemed colleagues on Anna Reuter, and you write or you suggest a potential black hole metric inspired by, for example, asymptotic safety in gravity. And all you do is to say, Francesco, let me just multiply. I choose for simplicity, because I mean, it's hard to solve quantum gravity, even for asymptotic safety. So I choose H equal to F. And then I multiply everything but this function here. This function is inspired by asymptotic safety. It's basically what they would say a redefinition of the Newton coupling constant. Then they kind of estimate this omega w, and this omega w by the first order corrections in Einstein, Hilbert gravity, and this has changed. The sign of the omega tilde has changed at least 3 times in the past 30 years. It's done through loop computations. But if you use this definition, you can show that psi1 is equal to θ1 by construction, but it's different from 0. And therefore, it violates the finiteness condition. If you actually calculate the Ricci scale at the horizon, it's infinite. And the question is, how come that there are 400 papers on the archive working on this model, even used to test or check the event horizon telescope or gravitational waves, and nobody has realized that. Anyone has a suggestion for that? I mean, it's pretty scary, right? That there are 300-400 papers on this, not checking that the Ricci scalar at the horizon is actually infinite. Wouldn't you think so?
Yeah,
I would think so. And the reason why, I can give you the reason why this was, was done is that because you have to self-consistently calculate D like I did it before, which is non-trivial. So this must be calculated from F, and F must be calculated from D. What most of the others, all the 400 people, authors that worked on that, many more, but 400 papers, they replaced for D the classical D, not the full quantum one. So they were not calculating the Ricci scalar at the horizon. They were calculating the Ricci scalar at another value, which wasn't the horizon, which turns out to be finite. But you were comparing apples and oranges, because it's much, much more complicated to calculate self-consistently. Is it clear now?
So are they still using this result?
Oh, yeah.
Because it's a 20.
Yeah, there are still papers coming out, basically almost every month. Yes.
So basically, any such kind of proposal go beyond the general relativity, which violates the constraints you found, is inconsistent.
Yeah, because you don't really have it.
Thank you.
Makes sense. So it also shows the power of the constraint. So they're not just, another set of, interesting things, but actually there's a universal. So you tell me you have a metric, you can check that. Now, I will also show metrics that do satisfy these constraints. And these are also very well-known metrics. This is the Hayward metric, which was introduced to, for example, cure the singularity at the origin, or the Dimnikova metric, which does the same thing, but with, if you will say, in the more fancy language, it uses basically instanton-like corrections. Now, these are also, to a large extent, random metrics in a sense that your guiding principle that you want to solve a problem. But I mean, there is no particular reason to use one metric with respect to the other. But they're famous metrics. I mean, that's been used a lot in the literature. You can show that these metrics do pass the constraints. So you can use them. They're models, but you will not consider them from the outset not, good solutions to some quantum gravity. Okay, fine. Then we also been playing a little bit with to find a minimal metric in terms directly of the Riddler distance that also satisfy all the constraints. So this was one of our proposals. I'm not trying to sell this. It's something you need to use just to say this is one way you can use. But now you see, as soon as I give you a metric, so I give you phi psi, I can actually calculate also the entropy. I can calculate the temperature, right? Now the temperature doesn't depend only on the coefficients, but I can say, as you were to expect, how it goes, for example, with the mass of a black hole. And it's actually reassuring that as you remember, the bigger is your black hole, the more classical it becomes. So the corrections are inversely proportional to the mass of a black hole. If you, on the other hand, are in the limit over small masses, then you will actually get closer to the Planck scale, and therefore you will have to take into account higher order terms. But now, because I know the temperature as explicitly as a function of the mass, I can calculate the entropy, and you get of course, the Schwarzschild result and corrections that go like the log of the mass of black hole divided by the black hole mass square. You often get logs because the S is integrated. Now, what I like about this approach is it's an approach where, I mean, not necessarily this model, but it is an approach that allows you to consistently take into account quantum corrections, okay? So if you want now, I've predicted the coefficients, but because I have a model for it. So different models will give you different prediction for the physical coefficients. Is it clear?
Yes, it's clear.
Very good. Now, I will not bother you, but we have also looked at the expansion at infinite distances. You also have, and now you're doing expansion not in the row per se, in a power series in row, but you're doing expansion in the inverse of the distance. Because, of course, at the infinite, you should recover Schwarzschild. Because, infinite distances, you have to have only the classical solution. So all the correction must be in phi and psi must be done 1 over d. Okay. And that's actually pretty cool. So now the coefficient of such things, I can constrain them. For example, requiring positivity constraints. I mean, this on property of your stress energy tensor. You don't have to, but if you do, you'll find also universal constraints on these coefficients. And it's pretty cool because now we have coefficients constraints on quantities which are physical, and then in principle can be tested. But for example, looking at how the planets go around a black hole, or actually even any star, as long as star is spherically symmetric and static, asymptotically it has the same method as a black hole. So if you're interested, you can go through it. It's something that requires some, I mean, per se will require probably 3 lectures to go through that.
Hello, can you hear me?
Yes. Yeah. Hi, Subir, how are you doing?
Oh,
Sorry, the previous lecture hasn't finished yet. So can you give us maybe 15 minutes?
Yeah, I'm sorry. I didn't realize my mic was on. Sorry to interrupt, Francisco.
No worries, Subir. Good to hear from you. All right. So now I will tell you something that we are doing now, and it will come out in presumably this month or next, is that I actually described how we can discuss black holes close, for example, to the horizon or infinitely far away. But now most of the properties, for example, going beyond the Hawking temperature, which is actually a local quantity, I would like to go, for example, at distances which are 3 times the radius of a black hole. Why do I want to do that? Remember in the first lecture, I told you I want to look, for example, at black hole shadow. And that I have to go at finite distances away from the horizon. So if you call the horizon the verge of your abyss, then I need to go beyond that. And how do I do that? With a metric that is basically expanded locally, typically requires many, many terms. Right? In fact, let me just look, and this I'm just giving a taste for it, right? I'm not gonna show you the paper, also because I don't wanna be scooped, but I'm gonna tell you actually this works with a simple example. So if you take the ordinary Schwarzschild, you find that you can extend your row in terms of, you can write your proper distance from the horizon in terms of the Schwarzschild coordinates up to a certain power in P. Now, if you plot the distance versus this row as a function of the distance with respect to exact result, the exact result is this one, okay? Now you see that it's well known, if you do a Taylor expansion, the convergence is pretty slow. Right? So Taylor 25 here means I have 25 terms to be able to describe the actual physical distance. Okay, so this will be your actual physical distance. You see that you really have to work hard to go further away. I mean, this is my dream. I would like to get at Z around 3, right? And in order to do that, you know, you can imagine how many terms I have to do. Clearly, many more than 25. So that will actually make the effective approach less effective if I want to describe some physical quantity at that distance. But fortunately, Padé has solved that problem for us. And he says, yeah, but you don't have to do a Taylor expansion. You can Padé resunder. So for example, if I do the same trick, but now with Padé summation, which you basically Padé, you rewrite your distance as the ratio of two polynomials. And then n and m are the order of the two polynomials, and p is the overall order, which means basically p tells you how many coefficients you need to well describe your system. And now you see that with 6 terms, not 30, I can go much beyond 3. Oh, but that's pretty nice, because it gives me an order of magnitude of the number of effective coefficients I need from my fundamental theory or my model-independent theory of black holes to actually describe physical quantity at finite distances from a black hole. So our paper to come will be basically a way to extend our approach to do real-life phenomenology. So the Padé approximants are compatible with Taylor series, clearly, and they lead to a quicker convergence of the series. Now, this is also related in many ways to resurgence, which is effectively a way of using in a smart way Padé approximants to understand the property of a series. Okay. So what do we have now? Well, we have access to physical quantities away from the horizon, and therefore we are stepping away from the abyss. We can calculate the shadow's radius and therefore the photon ring and do black hole imaging in a universal fashion, not depending on your underlying quantum gravity theory, but in terms of coefficients that are physical and that is basically can use to classify your quantum gravity theories. Can you still see? Yeah, you're still there? Hello? Hello? Hello?
I'm still here, Francesco, but they seem to have disappeared.
Just you and me, Subir.
There is Kaushar Paigo who is connected. I don't know if he's actually in Beijing or not.
Yeah, that I don't know.
Maybe reconnect. That might be best.
Yeah, but it's not us. I think them. We are connected to the actual Zoom. I think that's
Yeah, we are connected to the actual Zoom. So what happened? I mean,
yeah, I think they probably the system went down there.
well, okay, maybe they're
Never
trying to
much
reconnect to you.
about the calls. I mean, things
Yeah.
happen. How are you doing, Subir?
I'm fine, thanks. And you?
But not bad, not bad.
Okay. Are you in Naples or in Odense?
Denmark. So,
Yeah.
but actually, I'll be in Liverpool in 2 days. Tomorrow.
Sorry, Liverpool.
They're gonna be in UK tomorrow. Yeah.
Yeah. And they're back now, I think.
Yeah. Yeah. I can see ICTP-AP. Hello, can you hear us? Hello. Yep, I can see they're coming online again.
Okay, sorry, Francesco, we have some internet problem. So we missed what you said in the last minute.
Okay, so I guess you arrived from what I see. We arrived to all the approximants here, right?
Yes.
Okay, so let me just rewind this part. I hope I convinced you that now through the approximants, we can step away from the abyss and describe physical observables at finite distances from the black hole with a limited number of effective coefficients. This, we believe, is a breakthrough, which will allow us now to, in a pretty universal way, describe black holes and their corrections without the need of a specific model of quantum gravity. So we have now access to physical quantities away from the horizon. For example, we can calculate the shadow radius, the photon rig, therefore, and do some black hole imaging. We can now describe effective gravitational potentials, derive quasi-normal modes. All this quantity needed always to step away from the abyss. You needed to know the potential up to several times the black hole horizons. Now we can, okay? And eventually also describe gravitational waves. Now, you could say that at the bottom of your on my slide, you see that effectively you have to weigh against the accuracy of the PD with how many parameters you would like to use to be able to describe your system. Of course, the fewer the parameters, the better it is, but then you sacrifice accuracy. You actually can, in any case, measure the accuracy by studying the coefficients and how the PD approximants actually behave. So what next? So you will see in the next few months coming up a number of papers. One will be on how to handle charged and rotating black holes. In particular, the charged ones have this property of having the two, an internal horizon and an external horizon that can collide. And when they collide, you can have the Hawking temperature vanishes, and therefore your system are stable. This type of black holes are very relevant, for example, when people want to study swampland. Because again, these are also relevant for primordial black holes, not only for astrophysical black holes. Another thing you will see is that we're gonna soon, and actually again, it's a question of months maybe, also address the correction to the three-dimensional black hole. And if you ever heard about three-dimensional black holes, especially string theorists are very excited about that, because the three-dimensional black hole, also known as the BTZ black hole, can only exist in 3 dimensions if you have a negative cosmological constant. So they actually are ADS spaces. The BTZ black hole is non-singular at the origin, it's rotating, and it is asymptotically ADS2. And this actually has been one as the primary example for example, determining properties in 2-dimensional CFTs. Okay, so we would like to go beyond the Maldacena, classical quantum field theory limit, because now by including the quantum correction to the BTZ, you should be approaching the classic regime of your CFT. So we're very excited about that, as you can imagine. Phenomenology of this is also interesting. And then, eventually how to extend it to other gravitational objects, eventually wormholes and cosmology. And you can even do double quantum entanglement. What does it mean? Every time you heard about entanglement for black holes, effectively you had a classical black hole and quantum mechanics attached to a black hole. But now that you also have the quantum metric, now you have both. You can the quantum metric and the quantum particle system coupled, and so you can see the effects of both. I hope that I convinced you that you have an insane amount of applications, and you can provide universal constraints on the quantum gravity landscape via, for example, monitoring star orbits around black holes, quantum corrections of gravity waves in black hole mergers, and even an evaporation of primordial black holes. I will stop here, so I will not bite too much into a Subir talk. And thank you for your attention. I don't
Can we
think I
thank Professor Sannino for the interesting seminar, lecture? Any questions? Yeah.
Thank you for such an interesting lecture, Professor Sannino. I have maybe 2 questions to ask you. Can you hear me?
Yes, I can hear.
One thing is about, I have seen you using this effective quantum metric of black hole to calculate the quantum correction to the entropy. So, but as we know, so somebody also calculated the quantum corrected entropy for the black hole in some different approach. So have you ever compared this different approach in the coefficient of the logarithmic term?
Yeah, we compared. And if you use the same metric, you get the same results. Yeah, we did. I mean, it's,
So is exactly the same?
Well, no. I mean, many of these approaches that you were saying, they're specific models of quantum gravity, right? So in other words, if you use this metric, the Hayward, or use Diminikova, or use our metric, you will get a different correction to the entropy. So these are coming directly from the knowledge of the metric. Then there are some approaches, I think that's what you have in mind, where you, for example, from f of r gravity, where you actually write a truncated versions of quantum gravity, then you have to find the solution of your black hole, which is non-trivial. And if you've done it, then you can calculate the entropy. And in general, you do observe some log corrections in terms of the mass, but presumably 1 over chi squared, but this coefficient will be different. Make sense?
Okay, I see. Okay. And I have a second question is about, so do you think we can use, or we can solve some equation of motion for matter field, or even the perturbation of the gravity field on the effective quantum black hole metric? Do you think it can be used to solving some new equation of motion by some minimal coupling?
What I would suggest to do in that case, I mean, the consistent way of doing is to have a theory where everything is there from the beginning, and then you actually self-consistently solve everything from scratch. But as you know, this is insanely complicated because, I mean, you don't really know even how to handle the quantum gravity corrections, right? But what can you do is that now that I've given you a metric, you can solve the equation of motion of your particle states in the background of the metric here. So it's like doing quantum field theory and a non-trivial curved background. So if you allow this metric to be kind of your background, and then you add the particles as a mole deformation, they will actually, you can self-consistently do that. Make sense?
Okay.
That's the way I would do
Okay,
it.
thank you.
You're welcome. But thanks for asking. These are very interesting questions.
Any other questions? You have a question? Okay. Try to be brief.
Okay, okay, can you hear me?
Yes.
I have a question that you can calculate the entropy of the black hole, but how does the information encode on the black hole, especially the entropy is the cause entropy is proportional to its surface, the area of surface. How does the information encode as storage on the black hole?
Thanks for asking. I mean, we talked about it. So again, I don't have a proof of this, but my belief is that all the information are encoded in these physical coefficients here. So if you take can you hear me?
Yes.
So what I'm saying is that once you've written or rewritten your metric in terms of physical coefficients, right?
Yeah.
Then all the information is, because after all, you only observe the black hole from the outside, right? You cannot observe it from the inside. So then all the physical information, must be, all the physical information must be encoded in the actual physical values of these parameters.
Oh, by this, I see.
That's beautiful.
Yeah.
So now in the effective description, all the integrated knowledge has gone into this, in the physical coefficient.
Oh, you mean the information? Can I say that the information is is encoded in the matrix?
It has to be, right?
Oh, I see.
You all use the metric to calculate everything. Does it make sense? But now it's encoded in physical quantities, right? Which are expressed non-trivial in terms of the derivatives of the previous metric. I mean, when
because time.
Yeah, sorry, go ahead.
Go ahead.
No, I'm saying.
Yeah, just because time.
Yeah, I'm saying it again. That's fine.
You go ahead.
Yeah, so I would just want to say that, if you look at the outer horizon here, if you look at this paper, for example, in this, you have that the coefficients of the 1/d series these coefficients here are also physical. And these coefficients are, for example, have knowledge of the various conditions you put on, for example, positivity of your stress energy tense. And it puts constraints on these coefficients. And that's pretty nice. And so the physicality of the conditions are expressed into physical quantities you can compare directly to experiments. And that also encodes information of your underlying theory. Make sense? That's all.
Okay, thank you much. Due to the time limit, so let's thank Professor Sanino for the 2 great lectures.
Thank you. I appreciate your patience. Thank you for the invitation.
So thank you, Francesco. Thank you. Thank you for your lectures.
Yeah, you're welcome.
So yeah, see you later. Hope to see you next year.
Yeah, I would love that. Bye.
So bye. Goodbye. Bye. Okay. Our next lecturer, Professor Tobias Sakar, is already online.
Would you like to? Would the students like a little break?
Yeah, let's. But because we are already late, we just take a very short break. Let's continue at 5:15. Okay.
Fine. I'm here. So tell me when to start. Thanks.
Okay. Maybe. Yeah. Maybe can you share your slides?
Yeah.
We can test.
Yeah. Sure.
If it works.
1 second. Can you see them?
Yes, we can see it.
Very good.
It works. Okay.
Excellent.
So let's start in a few minutes.
Sure. So you had a full day of lectures.
Yes. Yes. So we're full of lectures.
Yes. Students must be a bit tired.
Yes, but we want to teach them a lot.
Indeed. Yeah. Is this the first time you are doing this school, or you have held it every year?
This is the first time of the school of the institute.
Yeah, that's
so
what I thought.
Yeah. We organize some short school, but on specific topics before.
Okay, I see. And these are all graduate students, or are they also including masters?
So most are graduate students. Most of them graduate students.
I see. All right. I suppose since it's on Zoom, people from other universities in China, etc., can also connect. But
not on Zoom because we don't, we don't want to mess it up. But it's
Okay.
broadcasting some China social media. So we
I see.
we broadcast your lecture is streamed online.
Oh, I see.
So they can watch online.
Yeah.
But
Okay.
they're
But
not
that
gonna enter the Zoom.
no, I understand. Is this on
We have
YouTube or something similar?
something similar, right? We have a camera here.
Yeah.
Okay. We probably should start. This is the last lecture of today. It's a long day, I would say, yes. We are very happy to invite Professor Subir Saka from the University of Oxford to give us 2 lectures. Professor Sakar is a world-leading top expert on particle physics and cosmology. The title of his lectures is, I think, challenging the standard model, standard cosmological model. Let's welcome him.
Thank you very much. Thank you. Yeah. Let me know when I should start.
Let me know. Yeah.
Okay.
When you're ready.
Yeah, I'm ready. Yeah. So, well, good evening to all of you. I realize you have had a long day, so this lecture will be perhaps more lightweight because I appreciate you are all doing theoretical physics and doing PhDs. So you are probably more familiar with theoretical aspects of what I'm going to talk about, but maybe less so the observational aspects. So I'll stress that more. And so I hope there'll be some pretty pictures, and so you can relax a little now. Okay, that's what I mean. So let me tell you what I want to talk about for today and tomorrow. It's about the standard model of cosmology, which is very important also for theoretical physics, because its dominant component is meant to be the quantum fluctuations of the vacuum, which is obviously the territory of fundamental physics. And it basically resuscitates the cosmological constant problem, which is at the boundary between general relativity and the standard model of particle physics or field theory. And therefore, I think it is important that theoretical physicists like yourselves understand what is actually involved when some astronomer friend of yours tells you that they have established a standard model in which the universe is dominated by vacuum energy density at the energy scale of milli-electron volts. This is their statement. How do they come to that conclusion? What is it about that that needs questioning? And what I'll do is I will present you some new observational evidence that uh, cast some doubt on this conclusion. I will not resolve any of the open questions in this subject, but I hope to make you think about these issues. Okay. So I should say that I was introduced to cosmology by this man here. His name is Dennis Sharma. He was a professor at Cambridge, then at Oxford, and then he went to CISA in Trieste. And he's pretty well known because his students are very famous. Stephen Hawking, for example, was his student. Roger Penrose was also somebody that he influenced very much. And I too came under his influence. And what I understood from him is that cosmology is not just a mathematical subject, it is something that can be applied to the physical world. And this is the quotation I've taken from his book, which says, before we ask the big questions, the why questions, we should first ask, how do you describe the world, which is the task of a physicist. So I hope that makes clear what my philosophy is in these two lectures. So a very brief recap of standard models of cosmology. They're nothing new. They've been around for thousands of years. For example, in China, ancient China, as you know, you had your own cosmology going back to at least 250 BC when the emperor burnt all the books. In Europe, there was this model due to going back to Ptolemy and Aristotle, in which the universe is basically as we see it on the sky. We are at the center of the universe, and around us are orbiting all the planets that were known at the time. And beyond that is the fixed sphere, the crystalline sphere, as they called it, of the stars. The stars don't move on the sky. And this model, I want to emphasize, was the standard model for 2000 years. Okay, it was not challenged. Even when new stars appeared on the sky, people did not record them because that was not meant to be happening. Such was the power of theory. Actually, in China, as you know, supernovae were recorded, but by the quote astrologers, there were no astronomers then. Now, what happened in the Copernican revolution was simply that the role of the sun and the earth were interchanged. Rather than the earth, the sun is now the center of the universe. Okay, but everything else, as you see, remains exactly the same. Now, if you fast forward to 100 years ago, when the first relativistic cosmological models were constructed, this so-called Copernican idea that we are not the center of the universe was extended further to say, well, the sun is not the center of the universe either. Everywhere is equivalent. Everywhere can be the center of the universe. Now, these are all philosophical ideas. And you might ask, why do we need any philosophy? Why can't we do everything by observation and experiment? Well, that's because in cosmology, it's different from the other physical sciences. We are restricted in what information we get about the universe just along our past light cone and within it, of course. We cannot move somewhere else in the universe, like here, and construct another light cone and see if we are seeing the same thing from there as from here, right? It's possible to do some indirect tests, but they are not yet practically feasible. So essentially, all our information is from one peculiar vantage point in the universe. And so we have to assume that this position is not special. Otherwise, we can't make any progress. And this goes by the name of the cosmological principle, which is simply that the universe must appear to be the same to all observers, wherever they are, right? It's like a democratic principle. I think seems to make sense. It was propounded by Mill, who was in fact the professor of mathematics here at Oxford. Now, by the time this principle traveled to Cambridge, they had to, of course, improve it. So they said Mill's principle is too restricted, namely that it is, the observations we make are independent of our spatial position, but they are still dependent on the time. Now, if you want to be more general, then we should not depend on time either. So our aspect should be independent of both space and time. And this was formulated as the so-called steady state theory of the universe, in which it has existed forever, it will exist forever. We are at no particular point in time, and also, of course, not in space. Now, this steady state theory was very elegant, but it was ruled out, as many of you know, by one simple observation. This was made in 1965 by these two people using that antenna at Bell Labs in Princeton. And they found that the sky is covered with this radiation uniformly all over the sky at about 2.7 degrees Kelvin. And that meant that the universe has had a hot, dense past. Okay, you can't create that radiation by, say, just scattering starlight, which is a possibility because the energy densities are similar, but that would not give you as perfect a spectrum for the radiation as was measured later by the Cosmic Background Explorer satellite launched by NASA in 1991. And in the first 8 minutes of data taking, Kobe already established that the spectrum is very close to a Planck spectrum. Now, it is simple to calculate that if you want to make such a good Planck spectrum, you can solve the equations of radiation transport. And it turns out that the only way to do it would be to have a very dense and hot plasma. And that means you can't do it today because the universe is today too transparent. So this ruled out the steady state theory and therefore the time aspect of the cosmological principle, but the space part still continued. And this is the quotation from the famous Steven Weinberg's textbook from which I learned cosmology. And he says, the real reason why we continue is not that this principle is necessarily correct, but we have to make a start. We have to assume something to look at the data. But if the data will not fit into the framework, then we'll be able to conclude that either this principle or the principle of equivalence is wrong. Nothing could be more interesting, right? Now, Steve wrote this in his textbook, back in the 70s, but it seems to have been forgotten that this is still a principle. It's an assumption. We have not proven it. So the modern standard model of cosmology is based on this principle. So this is actually from a computer simulation of the universe of structure formation. And what you see here is a universe in which structure is formed mainly in dark matter. And these tracery that you see here is the so-called cosmic web of galaxies and clusters and superclusters, extending out to what is really a Hubble volume, basically the size that we can see today within the causal universe. And what we do is we can start by assuming this cosmological principle, which tells us that the metric of space-time is maximally symmetric. It is of the so-called Robertson-Walker form. So I have written it here suggestively like a Minkowski metric by choosing to define something called conformal time, eta, which is related to the usual time t through a conformal transformation where a is the scale factor. So this metric is something that you can basically stretch with a scale factor radius a, and that is the only parameter in the model. Okay. Essentially, the evolution is self-similar. Now, if you adopt that metric, then you can construct from it the curvature tensor and reduce it to the Ricci tensor and so on. And Einstein tells us that the geometry of the universe, which is constructed from this metric and the Riemann tensor, can be related to the energy momentum on the right-hand side through Newton's constant. Now, what is this T mu nu? Well, in the old days when this business started 100 years ago, it was considered to be non-relativistic particles. They used to call it dust. Later, we realized that if you go back to the early universe, then radiation becomes more important than non-relativistic particles, but it's still matter. However, in the 1930s, it was realized that what we call matter are actually excitations of fields, quantum fields. And the quantum fields have 0-point energy. They're never at rest. And people like Zeldovich and then Pauli realized that these quantum fields contribute to T mu nu, a cosmological constant, which is it's a super renormalizable term in the Lagrangian. I'll come to it in a minute. Now, already in the Einstein's equations, we had a term lambda g mu nu. What is that term? That reflects the fact that this metric and this equation has an underlying symmetry, general covariance. Okay, you can make local coordinate transformations and nothing should change. And that means that you have the freedom to add a term proportional to the metric to the left-hand side of the equation, right? It's not anybody's choice. It is something that is allowed by the symmetry. It has to be there. And now, in field theory, we are saying that T mu nu also has a similar term, and the two terms should add together to give you a total cosmological constant, which is this little lambda plus the contribution from the fields. And it is this big lambda that then enters into the so-called Friedmann-Lemaitre equation, which tells you that this complicated set of equations, remember mu and nu are both running from 1 to 4. So there are 16 equations, but actually the metric has to be symmetric, right? Because the distance from A to B is the same as the distance from B to A. So therefore there are 10 equations, but the 10 equations reduce to just this one because of the maximal symmetry of this metric. And that tells you that the rate of change of the scale factor with time is related to the energy density in matter, that is rho sub m. And then the curvature of spatial sections of this metric, which is quantified by this quantity kappa or k. And then there is this cosmological constant, which is the sum of this geometric part and the contribution from the fields, right? I know this is all very simple and you have really done courses on this, but it is very important to take note of these things because people tend to forget that it is based on these assumptions that we have come to the very amazing conclusion that our universe is dominated by vacuum energy. So I want to emphasize this. Now what happens? These energy densities are scaling differently with the redshift. The redshift is simply the ratio of the scale factor when light was emitted to the time when it was received. And basically, it's a measure of the scale of the universe. And so the energy density of matter scales as the cube of the scale of the radius. So in other words, as 1 plus z cube. The curvature, you might intuitively realize, should go as the square. But the cosmological constant being a constant doesn't scale at all. So all I have to do now is to divide this equation throughout by h square, and then I get a sum rule relating the three components omega matter, which is rho m divided by 3h squared by 8 pi g, kappa omega k, which is k over h square a naught square, and omega lambda is lambda over 3h naught square, and these three add up to 1. Okay. So you have reduced all of cosmology to a simple sum rule. How did we manage to do this? Because we assumed maximal symmetry in the underlying metric. What allowed us to do that? The cosmological principle, the assumption that the universe is isotropic and homogeneous. Okay. Now, of course, the universe is not exactly isotropic and homogeneous. You can see in the simulation that it is all, inhomogeneous. You can see all the inhomogeneities, but it is still statistically inhomogeneous and statistically isotropic and statistically homogeneous. Okay, that's the idea. Now, there is a second equation called the Raychaudhuri equation, which has been reduced here to the simple form that the acceleration of the scale factor is minus 4 pi g by 3 times the gravitating energy density. So normally you only consider rho to be the energy density, but in general relativity, as you know, all energy gravitates, including kinetic energy, and pressure is just kinetic energy. So you have rho plus 3p. This is the only part where general relativity enters. Okay. And what that then means is that we can confront this set of equations with the data. And I'm sure you have heard this story many times, so I'll go through it very briefly. When we look at the expansion rate of the universe, the Hubble parameter, as a function of the redshift, we measure the brightness of supernovae I'll discuss this in more detail in tomorrow's lecture. We measured the magnitude of the supernovae and see how it varies with redshift. And the idea is that whether this expansion rate is slowing down or speeding up can be measured by looking at this. What it technically gives us is this quantity here, 0.8 times omega matter minus 0.6 times omega lambda. And what the observations are telling us is that this is slightly negative. Okay, the errors are large, but it is still negative. In other words, the universe is accelerating. If you look at the cosmic microwave background, there are these little fluctuations that have grown into that structure which you see in this picture. The typical scale of these fluctuations is 1 degree. So if I do a spherical harmonic analysis, then the power spectrum has a peak at a multiple of about 200, which corresponds to 1 degree, as you see here. And from this, you can work out that the curvature of space-like sections is very close to 0, because the actual scale that these patches will appear on the sky depends as the square root of omega k. These are all things you can look up in textbooks. I'm just reminding you of the basic features. Finally, we make measurements of things like clusters of galaxies or baryon acoustic oscillations, which are basically oscillations in the 2-point function of galaxies or their power spectrum, which is plotted here. It's very similar to these fluctuations, but it is much less marked. Here you see strong fluctuations. Here it is much less so, because the universe is actually not dominated by baryons, it is dominated by dark matter. So the fluctuations, which should have been very pronounced if it was only baryons, are now much less so. They're only about 1% in amplitude, but they can be picked out, and they give us a measure of the Hubble parameter as a function of Z and so on. And from all that, we can work out that the matter density is 0.3. So now when you put it together in this typical plot that you have seen, omega lambda versus omega matter, the radial line is omega lambda plus omega matter equals 1, because omega k is 0, so these two add up to 1. And then the supernova data is saying that I have to lie on this diagonal line here, omega 0.8 omega m minus 0.6 omega lambda is minus 0.2. And the matter density is saying that omega matter is around 0.3. So you see, we are supposed to be at the intersection here, where omega lambda is about 0.7 and omega matter is 0.3. So essentially, we are not determining omega lambda directly. We are determining by using this sum rule, right? By doing this little arithmetic here. And if you remember what the definition of omega lambda is, what this means is that lambda is of the order of h naught square. Okay, lambda, which is a fundamental quantity of nature and supposedly a constant, is actually being decided or set by the present day Hubble expansion rate, which is neither a constant nor fundamental. Why is this happening? It's because of the way we have chosen to interpret the data within the framework of this model, which has got only one dimensionful parameter, namely this Hubble parameter. But that parameter enters every observation we make in cosmology. So for all these reasons, one might be skeptical as to whether this quantity that we are saying dominates the universe is actually real physical phenomenon, or is it something that we are deducing simply because of interpreting the data in a particular simplified framework. Some might say oversimplified framework. So for particle physicists, the scales to remember are this Hubble's parameter, which is the inverse of 10 to the 28 centimeters, which is roughly the Hubble radius, the size of the universe, if you will. And in energy units, that's the infrared scale. That's 10 to the minus 42 GeV. Because as you know, in gravity, there's only one energy scale, which is this Gn, and Gn is very weak. So the corresponding energy scale is very large. The Planck scale is 10 to the 19 GeV. So you see, in this framework, you have a huge hierarchy between 10 to the 19 GeV and 10 to the minus 42 GeV, right? So it's very tempting to think of exciting things like, possible holographic connection between the infrared and the, the ultraviolet. Unfortunately, there is no de Sitter CFT correspondence. There is the ADS CFT correspondence, but it is not possible to define any connection so far. Nobody has succeeded between why the universe as a whole should affect the microphysics. So lambda is a microphysical quantity. H naught characterizes the universe as a whole. According to this framework, they're connected. This is, if it is true, this would be amazing, right? And people speculate all kinds of things, which I'll tell you about in a minute. But I hope I've got you intrigued now. Just to remind you that if I plot the scale factor as a function of time, the different solutions to those equations, effectively Einstein de Sitter is going asymptotically to infinity. Then you could have a universe which is pure de Sitter, which is expanding exponentially. You could have a universe called the Lemaitre universe, which becomes dominated by lambda, goes coasting for a while, and then takes off. So you see, at late times, since the matter density is redshifting away, the curvature is redshifting away, all that remains is lambda. So quite naturally, by construction, the universe will be lambda dominated at late times. This is not a surprise. We built it like that. But at early times, for example, when the microwave background decoupled at 300,000 years or so after the Big Bang, the description of the universe was very, very precisely Einstein de Sitter. It was omega equal to 1, k equal to 0 universe. Lambda was completely unimportant because at that time, which was at a redshift of 1,000, the matter density was 1,000 cube 10 to the 9, bigger than today, but lambda was the same. So it was completely negligible. So people keep talking about lambda CDM gives a very good description of the early universe. Neither lambda nor CDM is at all relevant in the early universe. It was dominated by radiation. So I think the field has become somewhat lazy. People use terminology without even thinking about what they're saying. So I would like that you don't make that mistake. So please pay attention to this. So to recap what I've just said, the cosmological principle is the foundation of this model. It's supposed to be dominated by lambda and undergoing expansion. Here is a pretty picture from the NASA publicity office, which you have all seen, showing what is supposed to have happened. Here we are, whatever, 13.6 billion years or something after the Big Bang. And we are supposed to know its components very well. So much dark matter, so much dark energy. Normal matter is only 5%, etc. This dominant part is rho lambda. Rho lambda is basically then lambda in Planck units. So in other words, lambda divided by 8 pi g, and lambda is h naught squared. 1 over 8 pi g is Planck mass square. So you see, it is actually the geometric combination of 10 to the 19 GeV and 10 to the minus 42 GeV. And therefore, you get something which is the geometric mean, 10 to the minus 12 GeV. Okay. And this is supposed to be the energy scale of the vacuum energy today. Now, we interpret this as energy density. What we see on the sky is actually just these observations are not giving us omega lambda. They're just giving us lambda. Okay. And then we interpret that as a energy density. This is important to remember. We have not so far seen any evidence for the negative pressure that should be associated with lambda. There are all these amazing satellites, WMAP, which measured the microwave background very precisely, and then Planck after it, and then the Sloan Digital Sky Survey from the ground. Now there are new instruments. The Dark Energy Spectroscopic Instrument recently published fantastic data on baryon acoustic oscillations. Next year, we will see first light at the Rubin telescope in Chile, which will do something called the Legacy Survey of Space and Time. And Euclid is in orbit. It is measuring the positions of millions of galaxies to detect weak lensing and so on. So great stuff, wonderful data coming in. But very little work has been done on testing the foundations of this model. And that's what I'll tell you about in the remaining time. So just to indicate that data has got so good that you can actually even measure the fact that the distribution of galaxies is not quite uniform on a scale of about 110 H inverse, so 150 megaparsecs. A parsec is 3.3 light years, and a megaparsec is, of course, a million parsecs. you can actually see a slight excess density of galaxies around any particular galaxy that you choose. And this is the remnant of those sound waves which were created in the early universe when the baryons and the radiation were coupled. And then at a few 100,000 years after the Big Bang, the universe became cool and transparent and they decoupled, and the sound waves have been spreading out. So now they are this far across. And the point is that this does not directly measure dark energy. It measures the Hubble parameter as a function of Z. And the CMB as well, I showed you that its power spectrum determines omega k, and this is a plot from the paper by the Planck collaboration. So you see it's measuring omega baryons, omega curve, cold dark matter, the optical depth to last scattering, the spectral index of the perturbations, and so on. But you don't see any entry here for lambda. Why? Because they don't measure lambda. Lambda is not imprinted on the microwave background. It was completely negligible at the time when the CMB decoupled. Okay, you infer it from that sum rule. Okay, and to determine lambda directly from the CMB, you have to do a different test, which is you look for the correlation of the CMB with large scale structure, and that is called the late integrated Sachs-Wolf effect. But this is a very, very faint effect, and it has not been yet seen at high significance. There are some confusing results about it. But the data is going to be soon with us. I think DAISY already has something of order 10 million spectroscopic redshifts. So we'll soon have a definitive test whether this late ISW effect is there. But meanwhile, we are stuck with this plot, which I showed earlier, where omega lambda and omega matter are constrained by the data. And observations like this BAO are therefore, as I'm emphasizing here, not a direct measure of omega lambda. So although the DAISY results recently even claim to measure a change in the equation of state, remember it is all done assuming the Friedman-Lemaitre-Robertson-Walker metric, assuming homogeneity and isotropy. They do not directly test it. So this is the example that I'm illustrating, that this is the DAISY data. You can see they've got very precise data of that little blip in the correlation function, which is the remnant of the sound wave. And then they say that they can actually measure the equation of state to be very close to that of of lambda. But then there is a indication for a non-zero evolution with redshift and so on, so on. But I'm trying to emphasize that the paper, if you look at it, starts by saying we assume a homogeneous and isotropic cosmology. They don't test whether this is actually correct. So now a brief interlude, since some of you are doing particle physics, or most of you, I suppose. What do you know about vacuum energy from field theory? Well, we have a wonderful field theory, the standard model, and we believe it is correct up to some cutoff scale. It's the effective field theory. But it is renormalizable. We have the gauge fields, we have the fermions, we have the Higgs. We have now trying to measure the potential of the Higgs field. But certainly all elements of the standard model are in place. And we can extend it by adding non-renormalizable operators, dimension higher than 4. For example, we already think we might have seen this term for neutrino mass, which is a Majorana mass. Need not be Majorana. The actual neutrino oscillations may be due to a Dirac mass. We don't yet know. We are also looking for proton decay, which can happen if you violate the symmetries of the standard model through these high dimension operators. And you can write down an infinite number of them, but they're all suppressed by powers of the cutoff in the denominator. And so they don't affect low energy physics. However, there are two terms which you can add to this Lagrangian which do affect low energy physics because they have the cutoff in the numerator. Okay. And the one that has attracted most attention in the last 40 years is this quadratic divergence of a fundamental Higgs mass, which you know about. And that diverges if the Higgs is truly fundamental. So, for example, the top quark is heavier than the Higgs, and that itself will give you a divergence to the Higgs mass, which goes as the quadratic, the square of the cutoff. And this creates a big problem, a naturalness problem for the standard model, because then there is no reason why the Higgs mass should be so light as 125 GeV. It should be pulled up to the higher scale. So a lot of models have been proposed. The idea that these corrections to the Higgs mass cancel, that is supersymmetry, or maybe the Higgs is not fundamental, maybe it's composite. Neither of these ideas have had any experimental evidence. But we are today concerned with this first term, which people talk less about because it has no relevance at all for laboratory physics. This is the quantum fluctuations of the theory. Strictly speaking, you can't calculate the absolute scale. You can only calculate differences, as you know, in field theory of the energy. But just dimensionally, you can see that since we have tested the standard model up to a TeV, there should be at least a TeV to the fourth power. And that's already 60 orders of magnitude higher than the energy density that the astronomers tell us the universe is dominated by. So if this were true, if this energy density gravitates, Einstein tells us all energy density gravitates, then imagine the universe is cooling down. It gets to the temperature of the electric scale, which is about 10 to the minus 12 seconds after the Big Bang, then this term should come to dominate. So there are two possibilities then. If it is positive, the universe will go into eternal exponential expansion, right? Or if the term is negative, and theoretically we can't even calculate the sign of this quantity, then it will collapse back to the Big Bang. So either way, you are never going to get a universe like the one we live in, which is over 10 billion years old and a huge universe expanding very slowly. This is not going to happen. We are never going to get past the point where we certainly know for sure that a field theoretical description is pretty accurate up to a TeV. This is the biggest problem, I think, in theoretical physics. Why are we here? As long as we accept our understanding of general relativity and of field theory, we should not be here. So this, of course, is the well-known cosmological constant problem. And the only person who has made a comment about it back in 1933, Pauli said, just what I mentioned a minute ago, that as is obvious from experience, the 0-point energy doesn't produce any gravitational field. Otherwise, you would not be here. But what happened in the last 100 years or 90 years is that theorists have failed to solve the lambda problem. We haven't solved it. So we just ignored it because it doesn't affect anything in the laboratory, it doesn't affect any experiments you do. So then the room was left open for astronomers to, stumble upon it. I say it is an accident waiting to happen that they finally discovered lambda in the universe at large, because lambda was built into the description of the universe at large, and it was the unknown parameter in the model which you determine by looking at the other parameters that you measure. So you determine lambda by using that sum rule, and that raises lots of problems. So for example, why are these two energy densities of the same order today? Because one is going as the cube of the redshift and the other is not going at all. So several thousand papers have been written on the possibility that this lambda is the vacuum energy of some slowly evolving scalar field. And you can see that this scalar field called quintessence needs to be very highly tuned, because its height is to be of order the vacuum energy scale, 10 to the minus 12 GeV. But it needs to be slowed down by the Hubble expansion. So if you look at the semi-classical equation of motion, its mass cannot be any higher than the Hubble parameter. So you see there is a 30 order of magnitude difference in the two energy scales. This is exactly the same fine-tuning as a bare cosmological constant. So you haven't actually solved anything. You have simply presented the problem in a new light. Okay. Similarly, you might say, I'll modify gravity on large scales. So maybe gravity propagates in more dimensions, and that's why it's so much weaker than the other forces. Very exciting idea, brain world. But then the question is, why do you modify gravity on the scale of the Hubble parameter? The only natural scale in gravity is the Planck scale. That is, again, 30 orders of magnitude smaller in the scale. So every attempt to explain dark energy essentially puts in the Hubble parameter by hand. As theorists, you know that if you really want a solution to something, you should not put in the answer by hand. That is cheating. That is not an explanation. And in fact, most recently, massive gravity created a lot of excitement. You can construct a theory of a gravity with graviton mass, but you have to give the graviton a mass of order the Hubble parameter for it to be relevant to cosmology. So again, you are putting in the answer by hand. So the only way to actually solve this coincidence problem is if lambda is of order h square, not h sub 0 square. Okay. But if you do that, then trivial to show that you are basically just rescaling the Newton's constant, right? Because you can then take this to the left-hand side and you can just change this by a factor of 2/3, which is not allowed empirically. And in any case, this won't give you expansion. So then the point is that do we infer lambda of order h naught square from observations simply because this is the only scale in the Friedman Lemaitre Robertson Walker model? This is my sort of understanding. Okay. And this enters in every observation we make. In fact, recently, and this might interest some of you, this actually came up back in 1983 when the first anomaly-free string theories were constructed. People realized that you can't have an S matrix in a de Sitter space-time because there is no future infinity. You don't know how to formulate this matrix. And since that is a fundamental object in quantum gravity, people have argued that any S matrix formulation would exclude de Sitter. You know, it will be forbidden by nature. And therefore, maybe there is a fundamental reason why you can't have it. And in fact, that is what has led to these ideas about the landscape of string theories. But this is a different topic. I'll leave that aside. Just to say for any anyone who's interested, that if that scale is actually a physical scale, 10 to the minus 12 GeV, the corresponding spatial scale is about 0.1 millimeters. So you might expect that something happens to gravity at that scale. And people have been doing very precise experiments trying to see if there's any deviation from the inverse square law at that scale. And so far, the answer is no. They have set a bound on a possible, say you add some equal-like term, the coefficient of the term has already got to be 10 times smaller than what would be the natural value. And these experiments are continuing. So there is no evidence that there is anything special about that scale. And similarly, there have been lots of proposed screening mechanisms. You know, people think of all these ideas that maybe this dark energy, you only can sense it away from matter. So there are chameleon mechanisms and so on. None of these have any evidence. They're all speculative ideas. So let me now come to the cosmology part with which you are perhaps less familiar. So this is our standard model of the evolution of structure in the universe. You start with these little fluctuations and last scattering, then they grow into the structure that we see today. And we have a nice picture in which these small fluctuations that we see on the microwave background, and we can describe by a Gaussian random field of scalar perturbations. The spectrum is almost scale invariant. In other words, there's the same power in each bandwidth of the wave number. And we like it because this is the kind of thing that should result from an early epoch of inflation. And so there is a whole description of how they could have grown into the modern structure just through gravitational instability. Now, to make this work, you have to realize that the amplitude of these perturbations is set by the microwave background, and the amplitude today is set by what we see on the sky. The question then is there enough time for these to grow into that? And the answer is no, unless you have dark matter, which is of order 10 times more than the visible matter, in which case the structure could have started growing before the universe became transparent. In baryons, you can only start growing structure after the baryons decouple from the photons. But if there was dark matter which doesn't interact with photons, then gravity can start growing perturbations in it before the universe becomes transparent. And you need that. Otherwise, you can't get from this picture to this picture. So this is actually the strongest requirement for dark matter. However, What it also makes clear is that the real universe today is inhomogeneous. So now we can ask, does it actually match this Friedman-Lemaitre-Robertson-Walker model? So this is a map of the local universe, which has been plotted by a group led by Brent Tully at Hawaii for many years. This is from the so-called Cosmic Flows 3 survey. We are at the center of this picture. We belong to this Virgo cluster of galaxies. These are just the overdensities which have been inked in. We are moving towards this so-called Shapley supercluster of galaxies. These thin lines are velocities. And what is being actually plotted is the peculiar velocity, which is the difference between our actual motion according to the redshift and what the velocity should be according to the distance and the actual motion. Okay, in other words, the non-Hubble component of the velocity is plotted. If you make the scale a bit bigger, this is going up to 200 megaparsecs. You notice it's all plotted in kilometers per second because that's what you actually measure spectroscopically. It's a spectral shift. We interpret that as a distance. If you look at larger scales, this is the Slow Digital Sky Survey that goes out to about 600 megaparsecs, and you see that tracery of structure, very similar to what you saw in that simulation, and that is what makes people think that those ideas, lambda CDM gives a good description of structure formation. But I can ask various questions looking at this picture. Can we actually approximate the universe as homogeneous very locally to us? Maybe it becomes homogeneous when you average over large scales, but is it homogeneous close to us? Then there is the question of whether, for example, are we typical observers? So does it not matter if you are in a dense region or in an empty region? Because gravity always responds to the local matter density. And then we can ask, are all the observed directions equivalent? Does it not matter if we look in this direction or this direction? Because surely it is the history along our path light cone that determines what we see. So these questions are rarely asked in cosmology. So let us do some tests. We are actually moving towards Shapley, apparently because something is pulling us. If there was no inhomogeneity, then we would all be in the co-moving frame. Nothing is moving towards anything else. We are just going away from each other in the Hubble expansion. So our peculiar velocity should fall off as roughly 1 by r, and we should converge to the frame in which the universe is isotropic and homogeneous. This is the idea. Why do we think that we are not in the right frame already? Because when you look at the cosmic microwave background, people tell you that it shows those little fluctuations, but actually that is not quite true. When you look at the cosmic microwave background, people tell you that it shows those little fluctuations, but actually that is not quite true. Can you hear me okay? I can hear an echo. Echo. All right, I'll continue, but speak less loudly. So this is the cosmic microwave background. The temperature of the microwave background is about 1 part in 1,000 hotter in this direction and 1 part in 1,000 cooler in this direction. Yeah. Now, this was actually predicted by Dennis Sharma because he realized that we were moving with respect to whatever frame the universe looks homogeneous and isotropic in, we are moving at a few hundred kilometers per second, which is a beta, special relativity beta factor of about 10 to the minus 3. So by special relativity and conservation of phase space density, we should see it hotter in the direction we're going and colder in the opposite direction. And Peebles and Wilkinson the following year gave this simple formula for how the temperature should vary over the sky, and it matches that very well. So we believe that the reason why you see this large dipole, which is 100 times bigger than those little fluctuations, is nothing to do with the early universe. It has to do with our motion today. Okay. And if we therefore boost ourselves by 369.8 kilometers per second, then we get to the frame in which the standard model of cosmology should work. Okay. But this supposition should be tested. If this is true, then as we go out further and further, roughly to a few hundred megaparsecs, we should actually go towards total homogeneity. And in fact, when people count galaxies in surveys, they say that actually the numbers do start scaling as the cube of the averaging volume on those scales. This is the received kind of knowledge. Why do we expect these velocities to die out? Because you can just construct a density contrast and using just Newton's equations, this is very local, there is no need for GR. You can just solve the continuity equation, Euler's equation, Poisson's equation for pressureless dust non-relativistic particles. That's what matters here. And if you look at the growing mode solution, I'm going a little quick through this because this is all very trivial for you. You can calculate the peculiar velocity field, which is just the inverse square law. You can see it goes as 1 by r squared, and integrate that to get the velocity. And since this peculiar flow that we are looking for, the deviation of the velocity field from the pure Hubble radial expansion, that's just the trace of the shear tensor. So then we can determine what it should be when we measure it using some particular window function that has to do with the nature of the survey. So for example, a volume limited survey will have a window function like that, a theta function, right? If you rewrite it in Fourier space, then it's easier to work with. And that same theta window function now looks like this. And if we then ask what is the variance of the Hubble parameter that you expect because of these inhomogeneities, I can calculate it by folding this whole thing with the power spectrum of the fluctuations that I see in the galaxy distribution. And here is a calculation we did some years ago of what this variance looks like. So you see on very small scales, say, on the scale of 20 megaparsecs, this can be of order, something of the order of 10%. Okay. But if I go to large scales, it falls off and should go below 0.1%. So beyond few hundred megaparsecs, as you can see here, the 300 by h megaparsec, it has dropped below the peculiar velocity variance has dropped below 100 kilometers per second. So in other words, in lambda CEDM, we can calculate how these variations should behave. The question we can then ask is, does the real universe look like that? So to do that, we looked at a compilation of supernovae. This was some years ago in 2011. This was then the biggest collection of supernovae. And what I've done is I've colored the supernovae according to whether their brightness corresponds to their distance or is brighter than where they are or less bright than where they are. Okay, the spot size is a measure of the discrepancy, right? Now, why we are doing this? Because we think that the local universe is not actually isotropic. If it was isotropic, then all these data points should vanish. Everything should be at the expected distance with the expected brightness. But we find that actually there is a dipole asymmetry in this, and we can do that in slices of redshift in order to determine what is the peculiar velocity in the local universe. And what we find is that there is a bulk flow in the local universe. There is a coherent motion which is moving at a 250 270 kilometers per second towards a direction which is not far from the CMB dipole direction, which is this little black spot here, right? The uncertainties in our direction are much bigger because you have only got a few hundred supernovae, whereas the CMB has got zillions of photons. But nonetheless, we can measure that velocity and we can compare it with the lambda CDM prediction, which is this blue line here. And you see that it is over, it's not dying out, it is holding steady. And other people earlier had also found the same. They had found a higher velocity even. However, the error bars are very large, and so the significance statistically is not very good. It's only about a sigma, right? So it is not so important. The important thing is that it is going out to about 300 megaparsecs to the Shapley cluster, and the flow is extending. And another collaboration called the Supernova Nearby Supernova Factory did the same analysis following us. And here they're showing the dipole in the supernova distribution on the sky, and they get a bulk flow very similar to us, 250 kilometers per second. If they look much further, to redshift range of order 300.06, about 300 megaparsecs, then the dipole becomes much fainter, simply because there isn't enough data there. This was closer to us. So what they do is that they say, what is the size of the object that you need to be pulling us at this velocity if I just assume inverse square law? Okay, it's a simple exercise you can do. And when you do this exercise, you can plot the mass of this attractor as a function of the distance that you're going out. And you see, you get this line here, this red band. And the Shapley supercluster is this green line. We don't know its horizontal, its actual spatial extent very well. So that's why it's a stretched out thing. And you can see that the Shapley supercluster is insufficient to explain the observations. You need something more. So in other words, lambda CDM is not giving you a good description of the local environment. And this has become very prominent in the last year or so, because people now plot that bulk flow as a function of the averaging volume, the radius of the averaging volume. The C11 as the measurement I showed you that we made, Collin et al. In 2011. But you see, the discrepancies are not that large. They're within 1 sigma or 2 sigma of the expectation of the lambda CDM model, which is this purple line. So, it is, something intriguing, but it is not a serious problem. However, recently there have been two measurements, one by the Sloan Digital Sky Survey, which got a measurement which is at least 2 sigma discrepant. And last year, there was a measurement by Cosmic Flows 4, which is very discrepant. Okay, you can see it is well out of the expected band for the standard lambda CDM model. In fact, they can quantify the discrepancy. It's almost 5 sigma. Okay, and this is something that is coming out of actual data. So people have concerns about how well you know the distances, because remember, you can't use the redshift to measure the distance. You're trying to measure peculiar velocities. So you have to have an independent measure of the distance. And these things are very hard to do in cosmology. So you have to use something called the Tully-Fisher method, or something called the fundamental plane technique, and so on. Or you use type 1a supernovae, as we did. But there are uncertainties. So this has now become an issue. Earlier, it had been a nagging problem, but not an issue, but now it's an issue. And the same kind of thing is showing up in other tracers. This is X-ray clusters, several hundred X-ray clusters mapped by ROSAT and Chandra satellites. And they have a luminosity distribution which is pretty well peaked. So they're like a standard candle. And the luminosity and the temperature should have a clear correlation in the model of clusters of galaxies which are emitting X-rays, because they've got hot gas in them held by thermal equilibrium. But you see that there is an anisotropy according to what direction in the sky you look. And that corresponds to a hot spot on the sky in, again, roughly the same direction. It's actually offset by about 30 degrees, but the uncertainties are large. So you can interpret this either as due to a 10% variation of the Hubble parameter, or a bulk flow going out to 500 megaparsecs, right? And so if I plot all the directions of these flows, they're all in the same part of the sky, close to the CMB dipole direction. And this is a problem. Okay, so I'll take another 10 minutes to just wrap up this lecture. And then in the next lecture, we'll continue with the supernova story. So at this point, we decided we need to do something different, something more fundamental, and something which is cleaner. So if you look at a good textbook, this is from Peebles, you will see that there's a picture of radio sources on the sky mapped from, I think, West Bank. This is in Virginia. And he says that this shows that the distribution of sources is isotropic around us. Now, for a long time, I wondered what that streak there is, whether it is some fault in the plate. It's actually our galaxy, because our galaxy also has radio sources. So there is a contamination, right? And these holes are there because these are the bits of the sky that you can't see from West Virginia. Okay. So this has been all, you're always trying to map the sky onto a two-dimensional plane. So there will always be this kind of matching issues. So you have to use some standard projection. Usually in cosmology, we use the Molly-White projection, but this is something to keep in mind. However, the statement cannot be correct. These objects cannot be isotropic. They must show a dipole anisotropy, same as the microwave background, because they are also at cosmological distances. Now, why is that? It's because of a phenomenon called aberration, which was discovered by Bradley, who was in fact the professor of astronomy at Oxford, many years ago. This is like, nearly 300 years ago. And essentially, long before special relativity, Bradley realized that the speed of light is finite. So when you look at a star, it is not where it actually is, because by the time the light has taken to reach us, we have moved. And the angle of aberration, the position at which you see the star, is therefore related to the true angle through our velocity. In fact, he made an estimate of the speed of light, which was good to, I think, 10%, back in 1728. Now, if you look at sources which have got some spectrum, the spectrum is typically a power law, and we have to also then take account of the fact that a moving observer is going to see all the photons Doppler shifted. So if you are moving in some direction, then the spectrum will be boosted towards the ultraviolet. So since the number of objects as a function of the flux is also following a redshift with the flux, we are going to see a different part of the spectrum and therefore be sensitive to a different number of objects. So if you put all this together, then you can work out that the anisotropy or the dipole that you should see for objects should be same as that of the CMB, which was V over C cos theta. But now there is a term multiplying it, which is 2 plus x times 1 plus alpha, where this is x and this is alpha. This is the index of the spectrum, and this is the index of the cumulative number distribution. So effectively what is happening is that if I consider the isotropic distribution of objects and I'm moving towards this red direction, then you can see in this bottom picture, slightly exaggerated, that there is a bunching of the points around that red point and a corresponding dilution in the opposite direction. And so the objects which are very close to the flux limit, they might be boosted above the flux limit in this direction and opposite in the other direction. So you get a dipole asymmetry. Okay. This is just pure special relativity. So you can't argue with this. Okay. We believe in this stuff. This has got to be there on the sky. And this paper by George Ellis, who is a well-known relativist from South Africa, John Baldwin, who was the head of the radio astronomy group at the Cavendish Laboratory in Cambridge. They met, as you see, at a conference in Crete, and they wrote this paper. And they pointed out that the velocity or the dipole that you see in the radio sources should match what you see in the CMB. This is a very powerful consistency test of the FLRW metric, right? Because the two things don't match, then either the radio sources are not cosmologically distant, or the CMB is not primordial, or the only third alternative is that we have something wrong with FLRW, right? Now, they said this in 1984, and today, now it is 40 years later, right? It has taken until now for this test to be done. So very briefly, I'll go through this quickly. What you need are objects at redshift more than 1, because you have to satisfy the first criterion. They have to be cosmologically distant. And we are after the kinematic dipole. There can also be a random dipole, because if you have a finite number of objects, then there can always be fluctuations. We don't want that. So you want a large number of objects, because this random dipole will decrease as 1 over square root of n. And there can also be a clustering dipole, which means that by chance, one of these objects might be close to us in that direction. Because as you saw, the distribution of all these galaxies, quasars, everything is inhomogeneous. So you have to make sure that they are really at a large distance. We need their redshifts. So to cut a long story short, we first did this with the first catalog of radio sources that was released only in this millennium by this is called NVSS. It was released by the Very Large Array, which is in Socorro, New Mexico. And we combined that with a catalog from Molonglo in Australia to make an all-sky map, which had short of 1 million sources. But that did not have measured redshifts, only estimated ones. The next thing we did was with galaxies, where we didn't know the redshifts, but the redshifts were not very high. So finally, you have done it with quasars, where the redshifts are high, and this is a much more definitive test. So very quickly, to show how it goes, you first make an all-sky map. You make sure that the maps are good, that they're clean, that in the overlapping regions of the two surveys, the counts are the same. You would remove any nearby sources by cross-correlating with other catalogs. These are all details that I won't go into. But then you see that dipole. You see that cos theta pattern, which you expect to see. There's only one problem. The amplitude here, you can already tell from the scale, is a lot bigger than what you expect from the CMB. Okay. So this is called the radio dipole anomaly, and Singhal had noted this before us. But if you do Monte Carlo simulations of how often you get to see this by chance, it's not that rare. The significance is only 2.8 sigma. So it is not definitive. And also the redshifts are not directly measured. So about 3 years ago, we got together with Nathan Secrist, who is a astronomer at the Naval Research Laboratory in Washington. He is on the celestial frame panel. They maintain the reference frame with regard to which all satellites operate. And von Hausegger, Sebastian, he is a postdoc here at Oxford. Roya Mohai and Jacques Collin are at the Institute of Astrophysics in Paris. They are my collaborators. And Ramiz is at the Tata Institute of Fundamental Research in Mumbai, in India. So he constructed this map of quasars on the sky. This was in 4 different bands, and we make sure we use 2 of them to ensure that what you're looking at is quasars. And part of the sky was looked at by the Sloan Digital Sky Survey. So you have measurements of the redshifts, very high precision redshifts, and you can see that they are definitely at redshift more than 1, right? We can say that 99% of them are at redshift greater than 0.1. So there is no question of any clustering redshift. And because the number is so large, the fluctuating the fluctuating dipole, the noise dipole is negligible. So you can now see when we smooth this map that there is clearly a dipole, there's a hot spot and a cold spot. And moreover, we know the distribution of the fluxes of these objects and their spectra, right? This is like 1.5 million objects. And these are astronomical details for those who are interested. We make a cut on the color to separate out quasars from other kinds of objects, because we measure this in 4 bands with this amazing satellite. It has just been retired after having operating for over a decade. And the spectrum of the object can also tell us the difference between an ultra-luminous infrared galaxy or a ordinary galaxy or a quasar, right? And then we make a cut on the flux to ensure that we have complete coverage, that there is nothing missing. Okay. And then we look at the picture very carefully. We have professional astronomers in our collaboration. They can look for trends with latitude and ecliptic latitude and so forth and take those out, so you have a very smooth map. So the bottom line is that we have a prediction for the amplitude and the direction, which is the CMB, the black star, and the expectation based on the formula that I showed you by Ellis and Baldwin is this vertical line. We do 10 million simulations of the mock skies, and that gives you this Gaussian here. The actual measurement is here. You see, the direction is consistent with the CMB, but the amplitude is not consistent. And we can now say that this is a 5 sigma fluctuation, because of all those 10 million simulations, only 5 actually got up to here. Okay. And that is when you start taking this seriously. So now we went back and looked at the radio sky as well as the quasar sky together, and we masked the radio sky with the radio map of the galaxy to make sure that we don't see any streaks on our picture like in the photograph from Peebles. And we lowered the threshold a little bit, we clean up further, and we find that the two dipoles are consistent. And in fact, we can now be generous and say we don't even care whether it points in the same direction. Let it point in any direction. We plot the dipole amplitude versus the offset from the CMB dipole. And these hotspots are the expectations, and these plus points are what we actually see. So we can, in a completely conservative way, without making any assumptions, combine the two data sets. So because they're totally independent, there's no overlap. And then we can reject the cosmological expectation at more than 5 sigma. So this was published in Astrophysical Journal Letters. And this is independent of the statistical method used. We are using frequentist statistics, but these people have used Bayesian statistics and they get the same answer. So this is the analysis by Dam et al. They also get, they actually get even higher significance. They get 5.7 sigma. And they show that their posterior is totally different from the prior that they have, and small changes to that like luminosity evolution make no difference. So they confirmed our answer independently. And another group actually did an angular power spectrum of the Catwise catalog. So what this is showing is the power in the multipoles as a function of the multipole. This is our measured dipole, whereas when you actually extrapolate the spectrum at large multipoles, which fits lambda CDM quite well, down to L of 2, this is the prediction for the clustering dipole. And you see it is much, much smaller than what we are measuring. Now, these people actually can even tell the difference between the departure of the linear theory from the nonlinear theory, and from that read off the so-called bias. So essentially, we know everything about the sample, and they agree that the clustering signal is excessive at large dipoles. So Tiwari, who led this work, is actually in China. He is at the Technion Institute in China. Then some people said you did a special relativistic calculation. Could there be general relativistic effects? Well, so we can do general relativity. We can look at the number counts in the standard formalism of formulating a bundle of null geodesics and asking what we should see. And to cut a long story short, we get the same answer as Ellis and Baldwin plus a little correction, which is negligible. It depends on the number density of the objects as a function of redshift, which we do know. I showed you this plot earlier, and this correction then turns out to be, less than 0.01%. So forget it. And it also shows that these people had raised the possibility that there's correlated evolution of those quantities which can mess up the answer. This is not true because you can think about it in physical terms. We are here, what we see on the sky is the projected result of all the physics that has been happening at earlier redshifts. So those observables capture everything. There can be nothing funny going on. Now, how does the community react to this?
Sorry,
Well, this is
sir,
GPBs.
I wonder.
I'm about to finish. Yeah, this is my last slide.
Okay.
So
Thank
people
you.
says this anomaly is as well established as the Hubble tension, but the literature on this is much smaller than the hundreds of papers about the Hubble tension. I expect the difference is an inevitable consequence of the way we behave. Okay, so I'll leave you to think about it, and I think I will stop here just to say that some theorists have paid attention to this work, and people have been constructing interesting models. You might want to think about these things too. So thank you. Sorry for going a little over time. I'll stop here. If there are any questions, I can take them.
Okay, we thank Professor Saka for the very inspiring lecture. Any short questions?
If we could, of course, also have the questions tomorrow. If you're running late already, I think they must be quite tired now. Okay, I can take one question. Sure.
Okay, okay, thanks for a very exciting lecture. So, what kind of mechanisms can generate this anisotropy dipole?
So The first thing that comes to mind is that, you know, there are anisotropic metrics you can consider, right? There are the Bianchi universes, for example, you know about them. The problem is that usually, as you also probably know, things like shear, vorticity, all properties, all those things decay very quickly with redshift. So it is very odd that this could be important today, but the early universe, like nucleosynthesis, cosmic microwave background decoupling, it all looks pretty simple. It does not. There's no evidence that there is any vorticity or you know, anisotropy at those times, right? So my suspicion is that this has only developed recently at redshift around 1. At the time when structure forms, structure starts forming at a redshift of a few, it peaks around redshift around 1. So this is associated with the creation of anisotropy in the universe. Okay. Previously, the universe was isotropic and homogeneous with small fluctuations. At late times, below redshift of 1, the density contrast starts getting you know, high. The universe becomes inhomogeneous, and that's when we are seeing this effect. So this probably, hopefully, I think, has no impact on the early universe at all. We can still consider that as isotropic and homogeneous. But the inference of cosmological constant and vacuum energy today, that is in question. Okay? Because that is based entirely on the assumption that things are isotropic and homogeneous today. And there is clear evidence that it is not. So as to how this anisotropy has developed, here are some papers which are considering those possibilities. I think it is fair to say that nobody has the full answer yet. This is a topic which is very open to new workers, you know. So especially for people like yourselves, if you're looking for interesting problem to work on, this is something that is, I think, very important and that has not had thousands of papers written on it. Like on quintessence and brain word and all that stuff, right? So I would encourage you very much to think about it. Thank you.
Thank you.
Okay, thank you much. Let's thank Professor Sarkar again.
Thank you.
So I will continue the second lecture tomorrow at the same time.
Thank
Okay,
you.
Thank you. See you
Bye
tomorrow.
for today. Ta.
All right. Okay, that's it for today. We continue tomorrow morning.